If you're in Orgo 1 or in Orgo 2, this video covers reactions for both. Now, for example, let's say if you learn the Diels-Alder reaction in Orgo 1. However, some of you may learn in Orgo 2, I don't know. So what I'm going to do is give you a list of topics in the order that I'm going to go through, and you could decide which topics that you've covered in class and which ones that you didn't. So you can pick and choose the topics, but the first topic I'm going to talk about and it's related to Orgo 1, and that's going to be reactions with alkenes, like your acid catalyzed hydration, hydroboration oxidation, oxymercuration, epoxidation. I'm adding HBr with peroxides and so forth. Um, After the alkene reactions, I'm going to go over a list of reactions associated with alkynes. And then I'm going to move on into substitution and elimination. This is going to be your SN2, your SN1, E2, E1 reactions. I'm going to give you a summary chart where you can easily identify if it's going to be SN2 or SN1. We're going to talk about the stereochemistry, if you get inversion or retention, and so forth. After that, I'm going to move on into reactions of alcohols, like what happens when you add HBr to an alcohol or SOCl2. I'm also going to go over some oxidation and reduction reactions of alcohols, like if you add PCC, what happens. If you add a Grignard reagent to a ketone, how it reduces to an alcohol, and so forth. Then I'm going to go over epoxides. If you open the ring with an acid or base, what type of product do you get? Do you get the more or less substituted one? I'm also going to go over reactions with ethers and acids. I'm going to talk more about the Grignard reagent, organolithium reagent, diabol, the Gilman reagent. We're going to review 1,3-butadiene when you have a conjugated system, when you get the thermodynamic product versus the kinetic product. We're going to talk about the Diels-Alder reaction after that. And then we're going to talk about reactions of aldehydes and ketones. This could be like acetal protecting groups, alkylation with LDA, how to know when you get an imine versus an enamine, the Wittig reaction or Wittig reaction, enolate ions, the haliform reaction, the HVZ reaction, so forth. And then I'm going to move on to reactions associated with carboxylic acid derivatives. This is going to be with your acid chlorides, your esters, your amides, your anhydrides. I'm going to do a few examples where the ring can open and when the ring can close and what type of products you'll get. So we'll go over that as well. After that, I'm going to move on to reactions associated with amines. This is going to be like the Hoffman and the Cope elimination, the Curtius and the Hoffman rearrangement reactions, the Gabriel synthesis reaction, reductive amination, and how to synthesize primary and amines from alkyl halides. After that, I'm going to move on to reactions associated with benzene. So this is like your bromination, your sulfonation, nitration, Friedel-Crafts, alkylation, acylation, when you get the ortho-para product or the meta product. And then finally, towards the end of this video, we're going to go over the aldol reaction, the Claisen reaction, the acetoacetic and malonic ester synthesis reaction, as well as the microreaction and the Romasin annulation reaction. So pretty much almost all the reactions that you've seen in organic chemistry, this video is going to touch on it. So let's go ahead and begin. So let's start with this reaction. Let's say if we have 1-butene with HBr. What's going to be the major product of this reaction? Now I'm going to go over the mechanism for this one because it's a very common reaction. The alkene is going to attack the hydrogen and is going to expel the bromine. Now you want to put the hydrogen on the less substituted primary carbon so you can get a more stable secondary carbocation. And then after that, the bromide will attack the carbocation. Now watch out for rearrangements. In this reaction, we're not going to get any rearrangements. Notice that this carbon is secondary and this is primary, and the carbon adjacent to the alkene is secondary. If this carbon here was tertiary, you can get a hydride shift. If it's quaternary, you can get a methyl shift, so watch out for that. But this reaction proceeds with Markov-Makar regiochemistry. The bromine went on the most substituted carbon. And because we have a carbocation, we can get a racemic mixture. The Br can be in the front, or it can be in the back. So make sure you're aware of that. So now what's going to happen if we add HBr with peroxides? This can be an organic peroxide, or you might see it as H2O2. So this reaction will proceed with anti-Markovnikov regiochemistry, meaning that the bromine is going to go on a primary carbon, which is the less substituted carbon. So now going back to 1-butene, let's say if we add HCl. And what about if we add HCl with hydrogen peroxide? Well, like HBr, HCl is going to put a chlorine on the secondary carbon, so it proceeds with Markovnikov regiochemistry. But if you add HCl with peroxides, you do not get the anti-Markovnikov product. You still get the Markovnikov product. Only HBr with peroxides will give you the anti-Markovnikov product. That reaction is specific for HBr. HBr is special in that case. The first step is exothermic, whereas if you use HCl with hydrogen peroxide, it's endothermic. It's not energetically favorable. So just make sure you know that only HBr with peroxides give you the anti-Markovnikov product. So now let's move on to another reaction. So let's say if we have a 3-methyl 1-butene, and what's going to happen if we add H3O plus to it? Now you might see this reaction as H2O with H plus. It's the same thing. Now notice that we have a tertiary carbon next to a secondary carbon. So this reaction proceeds via a carbocation intermediate. The OH is going to go on the most substituted carbon. So this reaction proceeds with rearrangement. We're going to get a hydride shift. Now let's say if we added BH3 borane with THF tetrahydrofuran and hydrogen peroxide and hydroxide. This is the hydroboration oxidation reaction. What do you think is going to happen? Well, after step 1, you're going to get a hydrogen on the secondary carbon and a boron group on the primary carbon. So that's known as an alkyl borane. And then after the second step, once you add hydrogen peroxide and hydroxide, the boron will be oxidized and it's going to be replaced with an OH group. This reaction proceeds with syn addition. The hydrogen and the OH should be on the same side, facing each other. Now the next one is known as oxymercuration demercuration. So we're going to have mercury acetate. Let me write that better. With water in the first step. And in the second step, we're going to use sodium borohydride. So here's the product for this reaction. We're going to get an OH on the more substituted carbon, but without rearrangement. So hydroboration proceeds with anti-Markovnikov regiochemistry. Oxymercuration demercuration proceeds with Markovnikov regiochemistry. We're going to put the OH on the secondary carbon. But none of these two reactions will rearrange. So make sure you're aware of that. By the way, the intermediate for the oxymercuration reaction, you need to know that you get this cyclic mercury acetate group. And then when water comes in, it attacks the secondary carbon, breaking this mercurinium ion. And eventually, after you lose the hydrogen, you're going to get an OH and HgOAc. That's after the first step. But once you add sodium borohydride, the mercury acetate will be replaced with an OH group. So, just to review, let's try this example. So what's going to happen if you add water with H+? And then if you add BH3 with THF, followed by hydrogen peroxide and hydroxide. Now for the oxymercuration reaction, we're going to change it a little. So we're still going to use mercury acetate, but instead of using water, we're going to change this part into methanol, CH3OH. And in the second step, we're going to use NaBH4. So for the first reaction, Notice that we have a primary carbon, this is secondary, and here this is tertiary. So we're going to have a hydride shift. The OH is going to go on the tertiary carbon. For the hydroboration reaction, because it proceeds with anti- or carbon-to-carbon chemistry, the OH is going to go on the primary carbon. And for the oxymercuration-demercuration reaction, we're not going to get an alcohol. Now, if you write water like this, what you need to do is if you take away an H, you get an OH. So water is going to give you an alcohol. But if you add an alcohol, if you remove a hydrogen, you're going to get the group that you need to add, which is an OCH3 group. And the oxymercuration reaction is going to put it on the secondary carbon. So it's going to go on the most substituted carbon of this double bond. By the way, what do you think is going to happen if, instead of adding water and H+, let's say if we added methanol and H+. Now this reaction too also can rearrange. And so the OCH3 group is going to go on this carbon. So now let's briefly go over the mechanism for the acid catalyzed hydration with rearrangement. So here's H3O+, we're going to draw it this way. Now the double bond is going to attack the hydrogen, and the OH bond is going to break. Because oxygen is more electronegative than hydrogen, when the OH bond breaks, the oxygen is going to pull those electrons toward itself. Now we're going to put the hydrogen on the primary carbon so we can get a more stable carbocation. Now this secondary carbocation is going to rearrange by means of a hydride shift. So as we put the green hydrogen on the secondary carbon, a plus charge will form on the tertiary carbon. And then at this point, water is going to react with the carbocation. Now, we're not done. There's another step that we need to consider. So here we have a plus charge. We need to use another water molecule to remove a hydrogen. And so that's how we're going to get an alcohol. So now let's talk about reactions that would lead to a methyl shift. So let's say if we have this compound, notice this carbon is quaternary. It's attached to 4 other carbon atoms. 1, 2, 3, 4. So now instead of using H2O with H+, we're going to use methanol with H+. So the H+ ion can come from sulfuric acid. This could be methanol with H2SO4. It's going to give you the same product. So the first thing that's going to happen is the alkene is going to attack the acid. It's going to grab a proton. And we're going to put the hydrogen on the primary carbon, as we've been doing so far. So now what we're going to have, instead of a hydride shift, we're going to get a methyl shift. And so the CH3 is now on the secondary carbon. We don't have to worry about the red hydrogen anymore, so I'm not going to redraw it. So now at this point, methanol, like water, is going to attack the carbocation. The reason why it does that is because the oxygen has a negative partial charge, and so it's electrically attracted to the partially positive carbocation. So here's the methanol that we added. Whenever oxygen has 3 bonds, it's going to have a plus charge. Now, just like in the last mechanism, we're going to use methanol again to remove a hydrogen. And so now we have our answer. So we have an ether as a product. Okay, so let's move on. Let's say if we have cyclohexene, and we're going to add bromine with dichloromethane. Sometimes you might see carbon tetrachloride, CCl4. This reaction would do the exact same thing. So bromine is going to add itself to the double bond, and the double bond is going to disappear. So you're going to get 2 bromine atoms, anti-addition. In fact, bromine is used as a test to test the presence of an alkene. So bromine has a red color. When it reacts with the alkene, the solution will go from red to colorless. So you know that you have the presence of an alkene. So make sure you know that. Sometimes that could be like a lab question. Now this is not the only product that you get. You're going to get the enantiomer as well. So you get two products in this reaction. Because sometimes they'll ask you, hey, does this reaction give you a meso compound, a pair of enantiomers? And it really depends on the carbon structure as well, but it usually gives you a pair of enantiomers for this particular reaction. But I'll talk more about that later in the video. So now let's start with cyclohexene again, but this time I'm going to add H2 and platinum. If you add hydrogen gas with a catalyst, it could be platinum, palladium over carbon, or nickel, the alkene will be reduced to an alkane. Now, because we have a line structure, we don't have to show the hydrogen atoms. But let's say if we use deuterium over a palladium catalyst, we do have to show it. You need to know that this reaction proceeds with syn addition. Now, notice that we have symmetry in this molecule. So therefore, if you were to draw the other product, you need to know that you don't get two products. You get one product in this example, even though it appears as if you can draw two. These are known as meso compounds due to the symmetry. So therefore, they're exactly the same. They're not different from each other. But here we have a pair of enantiomers. There's no symmetry across this line. So here you get two products as opposed to one product. By the way, when the bromines are opposite to each other, this is known as an anti-addition reaction. But when the deuteriums are on the same side, it's known as a syn addition reaction. So now let's move on to another topic. Starting with cyclohexene. What's going to happen if we use an alloy of zinc, copper, and diiodomethane? You need to know that this is the Simmons-Smith reaction, and it works by means of a carbenoid/carbene intermediate, and you're going to get this cyclopropane ring. So sometimes on the test, you might just see it like this. They won't show you the hydrogen atoms. You'll just see that cyclopropane ring, which is very unstable. You can also get the same product if you use diazomethane, and you need to activate it with heat or light. So this reaction too would generate a carbene intermediate. So here's what happens when you add the carbene across the double bond. Simultaneously, the double bond attacks the carbene and the carbene attacks the double bond. And so that's how you're going to get two bonds. And so you're going to get the cyclopropane ring. Now there's another reaction that does something similar. And in this reaction you can use chloroform, CHCl3, or even bromoform, CHBr3. Now if you use chloroform, your end product is going to look like this. You're still going to get the cyclopropane ring, but you're going to have two chlorines. One of the chlorines will leave. And you need a strong base because the strong base will remove this hydrogen. So here's what happens. Hydroxide takes away the hydrogen. And then you initially get this unstable carbanion, which spontaneously kicks off a chlorine. And then you're going to get a carbene. And so this is the intermediate that you have to add across the double bond. So now what's going to happen if you add osmium tetroxide with hydrogen peroxide? Sometimes instead of seeing hydrogen peroxide, you might see sodium bisulfate. So you can see any one of those two in the second step. So in the first step, you get something that looks like this, an osmate ester. Now it's rare that they'll test you on that, but you need to know the final result. After step 2, after you add hydrogen peroxide or sodium bisulfate, you need to know that you're going to get a diol, syn addition. So due to symmetry, this is a meso compound, so you only get one product as your answer. Now there's another reaction that will do the same thing. and that is potassium permanganate with hydroxides under cold and dilute conditions. And this will give you two alcohols in addition, so you get a diol. Now I want to contrast that with potassium permanganate under acidified conditions, like with H3O+, and usually this reaction is heated and it's concentrated. So if you see that, you need to know that it's going to cleave it, and it'll cleave it and create two carboxylic acids. It'll create a carboxylic acid if it's primary after cleavage. So here, this carbon is primary and this is primary. If you get a secondary carbon, it's going to be a ketone, and if it's just a methyl carbon, like one carbon by itself attached to no other carbons, it's going to be fully oxidized to CO2. But let's go back to the diols. So now you know how to make a diol with a cis configuration. But now we're going to talk about how to make a trans diol. So first, we're going to add a peroxy acid, RCO3H. Sometimes you might see this as MCPBA, or sometimes they may write out the formula. You might see like CH3CO3H. These are all different forms of a peroxy acid, but the end result is the same, and that is you're going to get an epoxide. Now once you add H3O plus to the epoxide is going to open, and it's going to turn into a diol, but anti-addition. Now let's talk about the mechanism for that reaction. So the epoxide grabs a H plus ion. You can grab it from H3O plus if you want, but it's going to be the same. And then after you protonate the epoxide, it can now open. So water comes in and attacks usually the more substituted side. But since they're equally substituted, it doesn't matter. I'll talk more about that later in the video. Once it attacks that carbon, the other OH goes to the front, but water attacked it from the back. So let's say if this OH is on the wedge, it is in the front, the other oxygen's in the back because it did like a backside attack. And so you get this. And then another water molecule comes in, takes away this hydrogen, and then you get the diol with trans or anti-addition. So because it's anti, you can get a mixture of enantiomers. So now what's going to happen if we use cyclohexene with NBS? Sometimes you might just see NBS by itself, you might see HV with it, you might see heat, or you may see peroxides. All of these can activate NBS. NBS is a reagent that slowly adds bromine to the solution, and the bromine reacts with the substance. But this is not a regular bromine reaction. This is a radical reaction. So I want to contrast that with this. So if you see like Br2 with HV or heat or peroxides versus Br2 with like CCl4 or CH2Cl2, they will do completely different things. So if you add NBS to an alkene, the double bond will not be affected. You're going to add a bromine atom on the allylic carbon, which is one carbon away from the double bond. Bromine with UV light and heat will do the same thing. It's going to be a radical reaction, and the bromine is going to be on the allylic carbon. Now, if you add bromine with carbon tetrachloride or dichloromethane, the bromine actually reacts with the alkene. Sometimes they'll put dark here, like it reacts in the absence of light. So this is a non-radical reaction. And you're going to get two bromine atoms, anti-addition. Let's talk about the mechanism for this reaction, because sometimes it's good to know because that reaction is very common. So in this reaction, the alkene attacks the bromine atom, which expels the other bromine atom, and this bromine atom attacks the alkene. Whenever you see two arrows like this, where the double bond attacks the bromine and the bromine attacks the double bond, you're going to get a cyclic intermediate. You're going to get a three-membered ring. So this is the brominium ion. And then the other bromide ion comes in, attacks from the back, and opens the ring. And that's why, because it does that backside attack, it pushes the red Br to the front. And the bromine that did the backside attack is now in the back. So that's where you get the anti-addition product. So now let's contrast that with a similar reaction. What do you think the major product will be if we add bromine and water? So here we have a secondary carbon, and this is a tertiary carbon. So what do you think is going to happen now? It turns out that the bromine is going to go on the secondary carbon, the less substituted carbon. And when you add water, we're going to get an OH on the more substituted carbon, but it's still with anti-addition. So we're going to get the enantiomer as well. Now, in the mechanism, once we get the brominium ion, which is going to look the same as in the last example, the water molecule is going to attack the tertiary carbon. The only reason why it does that is because there's a lot of partial charge on the tertiary carbon. And so it's going to push the bromine atom to the front, which is, it's over here. And the alcohol would therefore be on the back because it attacked from the back. But right now it's in the form of OH2+. And here's the methyl group. So right now that means the methyl's in the front, if you want to show the stereochemistry for it. So now another water molecule is going to come in and take away this hydrogen. And so you get this product. Now, if you're wondering why it attacks the tertiary carbon, you need to realize that there's a considerable amount of partial positive charge on this carbon. If we draw the resonance structure, we can take away this bond. And we're going to get a relatively stable tertiary carbocation. And so that's where the water attacks. So the water attacks here. But now keep in mind though, this form, this is the minor resonance contributor. So the actual resonance hybrid looks more like this molecule than this one. So when you show the mechanism, you show it in this form. This resonance structure is just so you can see why there's a lot of partial positive charge on this carbon. And that's why the water attacks that tertiary carbon, even though it's relatively hindered at that site. So what is the major product if we use 1-methylcyclohexene? And we're going to add chlorine with methanol to it. What do you think is going to happen? For all practical purposes, the chlorine, like the bromine, is going to go on the less substituted carbon, and the ether group, the OCH3 group, is going to go on the more substituted carbon. So we're going to get an OCH3 instead of an OH. But if we were to use water, this would have been an OH here. So keep that in mind. Now this is one that you might see on an exam. Let's say if you have this alkene and we're going to add BH3 THF with hydrogen peroxide and hydroxide. So sometimes you might see this as B2H6. That's simply a dimer of borane. That's called diborane. Now the end result is going to look like this. The CH3 will be in the front and the OH will be in the back. Now keep in mind, this is a syn addition reaction, but on an exam they probably won't show the hydrogen. So if you're comparing the methyl and the OH, it appears to be anti, but the reaction is syn addition when you compare the alcohol and the hydrogen. The hydrogen that was added is actually syn with respect to the alcohol. But on the test, you're going to see like the methyl and the OH, and they're going to appear anti, so just keep that in mind. So let's say if we were to use methyl cyclohexane again, but this time instead of adding BH3, we're going to use B2D6 with hydrogen peroxide and hydroxide. So if you see this, what you need to do is you need to put a deuterium atom on the more substituted tertiary carbon, and we're going to add the OH on this carbon, on the secondary carbon. But notice that these two are syn with respect to each other. The methyl is going to be opposite to the OH. So if the OH is in the front, the methyl is going to be in the back. It's going to be on a dash. So now what do you think is going to happen if we add, let's say, HBr to this particular alkene? Let's say if you have an oxygen next to an alkene. Well, what you need to know is that this carbon here, the beta carbon, is nucleophilic. This oxygen can form a double bond, pushing a negative charge here. And so now the oxygen bears a positive charge. And this carbanion is going to grab a hydrogen and expel a bromine atom. So now we're going to add the hydrogen to this carbon. And we still have a double bond here. So now the bromine atom is going to behave, well, I should say bromide. The bromide ion is going to behave as a nucleophile. It's going to attack this carbon, and then the double bond is going to break. So the end result is that we're going to add the bromine on the side that's closer to the oxygen, and the hydrogen's on the side that's away from it. So something you want to know, when you're adding, if you're adding an electrophile to this compound, the electrophile goes on the carbon away from the oxygen, which is known as the beta carbon. The alpha carbon, the nucleophile goes there. So I'm going to put N for a nucleophile. So your answer will look like this. So here's the nucleophile, here's the electrophile. In HBr, hydrogen bared the partial positive charge, so it was the electrophilic atom. Bromine bared the partial negative charge. And as you can see, in this form, bromine is nucleophilic when it has a negative charge. But sometimes bromine can be electrophilic. For an example, let's say if we use the same compound, but instead we're going to add Br2. So for bromine, it doesn't have a negative charge, so in this form it's electrophilic. So this oxygen is going to form a double bond, causing this double bond to attack the bromine atom. Let's use bromine and water for this example. Because if we add Br2, both Brs will be added, and that would defeat the purpose. But the first Br that we add is going to go on a beta carbon, where the electrophile goes. And so we have a double bond here. And then in this case, water is going to attack. Now water bears a partial negative charge, so it's going to behave as a nucleophile. It's going to go there. So now we have two lone pairs on the oxygen again. And then we're going to use another water molecule to get rid of this hydrogen. So if you add bromine and water, the OH goes on the carbon that's closer to the oxygen, and the bromine goes away from it. So let's consider another example. So what if we add bromine and, let's say, methanol instead? So the mechanism is going to be very similar. The bromine is going to be the electrophile. It's going to go on the electrophilic position. And the alcohol will go here, but in the form of an ether after you lose the hydrogen. So now, what if we only added an alcohol? and no bromine in this example. So let's say if we just added methanol with an H plus catalyst, what's going to happen? Well, in this case, the final answer is going to look like this. The methanol is still nucleophilic, so we're going to add the nucleophile over here. So you might be wondering, hey, so what is the electrophile? It turns out the electrophile is the H plus ion, so we're going to add a hydrogen on this carbon. So if we were to work through the mechanism, this double bond will first grab a hydrogen. And so here it is. And then methanol will now attack this carbon. Okay, so for our last step, we're just going to use another methanol molecule to get rid of the hydrogen. And so we're going to get this compound. So sometimes you might see something like that on the test. Now let's talk about stereochemistry in terms of when you get meso or enantiomers and so forth. So if you have a cis alkene and a syn addition reaction, you're going to get a meso compound if the molecule is symmetrical. If it's not symmetrical, it's going to be a pair of enantiomers. If you have cis and an anti-addition reaction, you're going to get a pair of enantiomers, regardless of the structure. If you have a trans alkene plus an anti-addition reaction, you can get a pair of meso compounds if the structure exhibits symmetry. Trans plus syn would yield a pair of enantiomers. So keep that in mind as we go through the next set of reactions. So test your knowledge. Let's say if we have cyclohexene, what is going to be the major product if we add potassium permanganate with hydroxide under cold and dilute conditions? Now, if you remember correctly, this is going to give us two alcohols, or a diol, syn addition. So here we have a syn addition reaction and a cis alkene, and the molecule shows symmetry, so we're going to get a meso compound, which means we only get one product. Okay, so now let's look at our next example. Let's say if we add D2 with a platinum catalyst. We know we're going to get an alkane and two deuterium atoms, syn addition. So here we have, I guess you can call it a cis alkene, and this is like a syn addition reaction, but notice that we don't have symmetry because of the methyl group, so therefore it can't be meso. We're going to get a pair of enantiomers. Alright, so now let's say if we have a cis alkene and we're going to add Br2 in the presence of carbon tetrachloride. So we know it's an anti-addition reaction. So cis plus anti would give you a pair of enantiomers. As you can see, there's no symmetry here. Now let's say if we were to use a trans alkene, what is the stereochemical relationship of the products? Let's use dichloromethane this time. So this will put two BRs, anti with respect to each other. So we have a trans alkene, an anti-addition reaction, and as you can see, there's symmetry about that line. So this is going to be a meso compound. Now what about this example? Now notice that across the double bond, here you have a methyl group, but here you have an ethyl group. You can see that it automatically lacks symmetry. So you know that you cannot get a pair of meso compounds, or just you can't get a meso compound. You can get a pair of enantiomers. A methyl compound will always be one product. It will never be two. So now let's go into alkynes. So let's say if we have 2-butyne, and we're going to add hydrogen gas with a palladium catalyst. Go ahead and write the reaction for that problem. Feel free to pause the video and see if you can get it. If you add hydrogen gas to an alkyne, it's going to reduce to an alkane. If you add sodium metal and liquid ammonia, you're going to get a trans alkene. If you add hydrogen gas with a deactivated palladium catalyst, where it's poisoned with barium sulfate and quinine as a solvent, this is the Lindlar's catalyst. It's just written in a different way. And you're going to get a cis alkene. So make sure you're familiar with that. I'm going to put LC for Lindlar's catalyst. And here we have a trans alkene. So those reactions, you simply just have to know it. So here we have 1-butyne, and what's going to happen if we add R2BH? This is similar to borane, which was BH3, but for alkynes, there's only going to be one hydrogen attached to it. And then with THF, hydrogen peroxide, and hydroxide. What's going to be the major product? So this is going to go down to an alkene. And initially, you're going to get an alcohol on the primary carbon. So this reaction proceeds with anti-Markovnikov chemistry. So this is called an enol, but it's going to tautomerize into an aldehyde. So this is the final answer. This is what you need to draw as your major product. Now these two are in equilibrium, but the aldehyde form is more stable than the enol form. But just know that you do get the enol as an intermediate. Now let's say if we were to use the same alkyne, but this time we're going to use mercury sulfate with water and sulfuric acid. So initially we're going to get an enol as well, but the alcohol will be on the secondary carbon rather than the primary carbon. So we have Markovnikov chemistry, and then this is going to tautomerize into a ketone. So we're going to get a ketone as the final product instead of an aldehyde. So now let's work on some alkyne synthesis reactions. Let's say if we have acetylene, what's going to happen if we add sodium amide, NaNH2, with methyl bromide? What do you think the major product will be? Well, you need to know that the NH2 minus ion is a very strong base, and so it's going to remove a hydrogen. And so you're going to get the acetylene ion, which is nucleophilic. The carbon has a negative charge. And then we're going to react it with methyl bromide. This is going to be an SN2 reaction. And so all we're going to do is, well, the only thing that we did here, what we've accomplished, is we're replacing the hydrogen with the methyl group. So with that in mind, go ahead and predict the major product of the following reaction. So in step 1, we're going to add NaNH2. In step 2, we're going to add CH3Cl. And then step 3, we're going to add NaNH2 again. And in step 4, we're going to add CH3, CH2Br. So notice that there are two hydrogens that we can remove. So we're going to replace this hydrogen with the methyl group in the first two steps. Next, between steps 3 and 4, we're going to replace the left hydrogen with the ethyl group. And here's the methyl group for the one on the right. So the final answer will be CH3, CH2 with the alkyne in the middle, followed by the CH3. So sometimes you're going to have to find the missing reagents. So let's say if your final product look like this. What reagents do you need to make that product? So step 1, we need to add NaNH2. Step 2, look at one side of the alkyne. So let's focus on this side. There are 3 carbons. So we need 3 carbons and maybe like a leaving group. We're going to put a bromine. Step 3, we need NaNH2. And then step 4, notice the left side. We have a tert-butyl group plus 2 extra carbons. So here's the tert-butyl group. 1, 2, and then a Br. So basically you just draw what you see, then add a bromine or chlorine to it. And it's going to give us that product. Now, let's say from this alkyne, we want to make the following compounds. Because sometimes it doesn't stop there. I got to make sure I have the right number of carbons. Let's see. 1, 2, 3, 4, 5, 6, 7. I believe I counted that correctly. Okay, so what extra reagents do we need to make those following compounds? So on the left, we want to convert the alkyne to an alkane, so we're going to use hydrogen gas and palladium. In the next one, we want to get a transalkene, so we're going to use sodium metal with liquid ammonia. You can also use any alkaline metal like lithium metal too, that can work as well. And for the next one, to get the cis alkene, we're going to use hydrogen gas with the limitless catalyst. And for the last one, we want to get a ketone. Now notice that both of these carbons are equally substituted. They're both secondary. So we can use hydroboration or the one with mercury sulfate. So let's pick mercury sulfate with water and sulfuric acid. So that's how we can make those particular compounds. So now let's talk about ozonolysis. Let's say if we have an alkene, and let's say if we add ozone with dimethyl sulfide. What do you think the major product will be? Well, what you need to do is you need to cleave the alkene and add 2 carbonyls to it on both sides. So on the left side, we're going to get a ketone. On the right side, we're going to get an aldehyde. Now, let's say if you were to use potassium permanganate with H3O+, and let's say it's warm and concentrated. Well, you're going to cleave it the same way. But notice that here, when it's secondary, it's going to stay a ketone. But if it's primary, instead of being an aldehyde, it's going to be fully oxidized to a carboxylic acid. So that's the difference between those two. So now let's say if we have a terminal alkene. What do you think the major products will be if we use ozone and dimethyl sulfide versus acidified potassium permanganate, heated and concentrated? So we're going to cleave it here. But if you have a terminal alkyne, it makes it easier if you draw the 2 hydrogen atoms that are here. So on the left side, we have an aldehyde, so there's 1 hydrogen here. And on the right side, we have formaldehyde. So ozone reacts with alkenes to make ketones and aldehydes, that's it. Potassium permanganate can make a lot of stuff. So here, this is primary. That's going to be oxidized to a carboxylic acid. And this carbon that's by itself will be fully oxidized to CO2. Now sometimes the alkene may be within a ring. So what's going to happen if we add ozone with dimethyl sulfide versus acidified potassium permanganate? So just like before, we're going to cleave this alkene. And so we're going to get a ketone there and an aldehyde here. So you can turn this into a straight chain if you want. We have a total of 8 carbons, actually 9, I miscounted that. So this is carbon 1, 2, 3, 4, 5, 6, 7, 8, 9. And on carbon 6, this should be a ketone. The K is in the way. Now, let's say if we were to use potassium permanganate. The ketone will be unaffected, but the aldehyde, which is primary, will be oxidized to a carboxylic acid. So this would be the product instead. So now let's say if we have an alkyne. What's going to happen if we add ozone to an alkyne? In this case, ozone and potassium permanganate will have the same effect. The alkyne will be cleaved, and you will get carboxylic acids. So now let's move on to substitution, elimination, and those reactions. So let's make a table first. So on this side, we're going to have the substrate. I'm just going to put sub for substrate. And I'm going to make 4 columns. So here, this is going to be a methyl substrate, so I'm going to put like CH3Br. And then we'll have a primary alkyl halide, and then a secondary alkyl halide, and finally a tertiary alkyl halide. So in this column, we're going to have a protic solvent, like methanol, water, or even ethanol. So when you see ET, that means ethyl, 2 carbons. In the next column, we're going to have the mixture of a good nucleophile like iodide, cyanide, or even a sulfur with a negative charge, with a polar aprotic solvent. This could be like DMF, acetone, HMPA, crown ether. All of those are polar aprotic solvents. Now, in the third column, we're going to have a strong base like hydroxide, methoxide. The key distinguishing feature here is the oxygen has a negative charge and it's not delocalized. Ethoxide will be part of this category. So if we compare column 1 and column 3, they look very similar. In column 1, we have CH3OH. In column 3, CH3O-. Sometimes you might see the combination of both together. You might see CH3O- on top, CH3OH on the bottom. In such a situation, this one has priority. When the oxygen has a negative charge, it reacts way more faster than a neutral oxygen. So when you see both elements, like both compounds, both substances from the 2 categories, the strong base takes priority. So column 3 has more priority than column 1. Now in column 4, we're going to have a very bulky base, strong and bulky, so it's going to be like terbutoxide. So sometimes you might see it as TBUOK, which stands for potassium terbutoxide, and usually it's dissolved in terbutanol. Now, anytime you have a methyl substrate, it's always going to be an SN2 reaction. You cannot have an elimination reaction with a methyl substrate. To form a double bond, you need at least 2 carbon atoms. Now, if it's primary, the major product will be an SN2 reaction. However, if you use a very bulky base, the major product will be an E2 reaction. If it's secondary or tertiary, the use of any strong base, regardless if it's bulky like terbutoxide or if it's small like hydroxide, will be an E2 reaction. Now, when it's secondary, if you have a good nucleophile and a polar aprotic solvent, it's going to favor an SN2 reaction. If you have a protic solvent like the first column, it's going to be a mixture of SN1 and E1. If it's tertiary, it's going to be SN1 and E1 unless you have a strong base. So make sure you know that SN2 reactions proceed with inversion of stereochemistry. SN1 reactions, you get a racemic mixture. SN1 and E1 reactions, because they proceed via a carbocation intermediate, rearrangements are possible. So I'm going to use capital R for that. For an E2 reactions, there are no rearrangements. And for SN2, there are no rearrangements. The SN2 and E2 reactions are concerted reaction mechanisms. They occur in one step. All bond breaking and bond formation occurs simultaneously. Now, you need to know that if you use column 3, if you use a strong but a non-bulky base, it's going to give you the Zaitsev alkene. The Zaitsev alkene is simply the most substituted alkene. For the E2 reaction, if you use a bulky base, you're going to get the Hoffman alkene. That's the less substituted, less stable alkene. The Zaitsev is the more stable, more substituted alkene. Now, for the E1 reaction, it also gives you the Zaitsev alkene. So those are some things to know. So let's go over some reactions at this point. So let's start with methyl bromide. So if we have methyl bromide, and if we use potassium terbutoxide, what do you think the major product is going to be? Well, anytime you have a methyl substrate, it's always going to be an SN2 reaction. This is the one time terbutoxide can be used to make an ether. And this is the product that you get. So now let's say if we have 1-bromobutane, and if we add sodium hydroxide dissolved in water. Even though water is in column 3, water is in column 1, sodium hydroxide is in column 3. Column 3 has more priority over column 1 when they're both mixed together. So when you put hydroxide, it's going to favor an SN2 reaction because we have a primary alkyl halide. The reason why it's primary is because the carbon that the bromine has is attached to only one other carbon. So now the hydroxide is going to approach the carbon from the back. The reason being is it's repelled by the partial negative charge of the bromine atom. So as it attacks the carbon from the back, it's going to expel the bromine atom. And so we're going to get an alcohol. Now to contrast that, if we were to use terbutoxide, potassium terbutoxide with terbutanol, we would get a different product. Because we have a bulky base, it's going to favor an E2 reaction rather than an SN2 reaction. And in an E2 reaction, the base will grab a hydrogen, the carbon-hydrogen bond is going to break, and it's going to form a double bond. So in this case, we're going to get 1-butene. Okay, so let's try this particular reaction. Let's say if we have 2-bromobutane. What's going to happen if we add potassium iodide and acetone? So we have a secondary alkyl halide. In this case, anything can happen. It could be SN2, it can be SN1, E1, or it can be E2. So you have to really look at some other factors. Iodide is a very good nucleophile, and acetone is a polar aprotic solvent, meaning it doesn't have any OH or NH bonds. And as a result, this is going to favor the SN2 reactions. Polar protic solvents favor SN1 and E1. Polar aprotic solvents favor E2 reactions. And so the bromine atom is going to leave, and we're going to have inversion of stereochemistry. So keep in mind, iodide is a better nucleophile than bromide, which is better than chloride and better than fluoride. This is true in a protic environment. So the nucleophilic strength increases this way. By the way, in an aprotic environment, fluoride is a better nucleophile than iodide, so make sure you're aware of that. So now in our next example, we're still going to use 2-bromobutane, but this time we're going to add H2O. So if we add water to a secondary alkyl halide, what's going to happen? Water is a protic solvent, and so we're going to get a mixture of the SN1 and the E1 reaction. So let's focus on the SN1 product. Because it's chiral, we're going to get a racemic mixture. So whenever you add water, you're going to get an alcohol. You're going to get the inverted product with the OH in the back, and you're going to get the retention product with the OH in front. So this is going to be an unequal racemic mixture. You get more of the you get more of the inverted product compared to the retention product. So you don't get an equal racemic mixture, but you get an unequal racemic mixture. So make sure you keep that in mind. Now for the E1 reaction, you can get two alkenes, a double bond on the left of the carbon-bromine bond and on the right. However, they're not equally stable. This alkene is known as the Zaitsev product, which the E1 will give you this as the major product. And this alkene is known as the Hoffman product. That's the less stable alkene. Internal alkenes are usually more stable than terminal alkenes. Now, the more R groups an alkene has, the more stable it is. This alkene has 3 hydrogens, so that means it only has one R group. This alkene has 2 hydrogens, so that means it has 2 R groups. So here we have a disubstituted alkene, one of 2 R groups, and this is a monosubstituted alkene. Disubstituted alkenes are more stable than monosubstituted alkenes. Also, if you need to find all the possible products, you need to watch out for E and Z in cis and trans. Notice that this alkene, we have the trans form. We can also get the cis product as well. But trans is more stable than cis, though, so this will be the major product still. But now let's talk about the mechanism for this reaction, because sometimes you're quizzed on it. In an SO1 reaction, the first thing that happens is that the leaving group leaves, and we're going to get a carbocation. At this point, a rearrangement can occur depending on the carbon structure. So we have a secondary carbocation, and there are no tertiary or quaternary carbons next to it, so no rearrangements will occur. So now, once we add water, water is going to attack the carbocation. And then we're going to have an oxygen with 3 bonds and a plus charge, and another water molecule will come in and remove a hydrogen, giving us the alcohol. Now, water can attack from the front or it can attack from the back. Now, we said that the inverted product was about 60%. Sometimes it could be 70%. And the retention product was 40%. When it attacks from the front, we get the retention. If it attacks from the back, we get inversion. The reason why we get more inversion than retention is because the bromide, it doesn't leave too far away from the carbocation. It forms like an ion pair, so it stays close by. And so oxygen, which has a partial negative charge, is repelled by the bromide ion. So that repulsion kind of slows down the water from attacking from the front side. And that's why we get a little bit less retention, more inversion. When it approaches from the back, there's nothing to stop it from attacking that carbocation. So now let's focus on the E1 reaction. In the E1 reaction, the first thing that happens is the leaving group leaves, and we're going to get a carbocation. Now we're going to focus on the major product, but let's draw the different hydrogens that are out there. So we have a blue hydrogen, a red hydrogen, and a green hydrogen. Now, if the base takes away the blue hydrogen, we're going to get the alkene on this side. So that's going to be the minor product. If it takes the red hydrogen, we can get like a trans alkene. And if it takes the green hydrogen, we can get the cis alkene. So depending on which hydrogen is removed, you can get different alkenes. But we're not going to get into too detail in terms of when is the cis or when is the trans, but just know that you can get a mixture of those isomers. But here's how you finish the mechanism. So water, instead of acting as a nucleophile, it can act as a base. It can, let's go for the red hydrogen. It can grab the red hydrogen, and then the carbon-hydrogen bond will break, and then so we get the trans alkene. So now going back to 2-bromobutane, what's going to happen if we add a strong base but not a bulky base? So let's use sodium methoxide and methanol. So column 3 has more priority than column 1, so it's going to be an E2 reaction. Now it's not a bulky base, so we're going to get the Zaitsev product. So that means we're going to remove the blue hydrogen. We're not going to remove the primary hydrogen. So the base is going to grab a hydrogen, we're going to get a double bond, and then the Br is going to leave. So we're going to get this alkene product. Now keep in mind, you can also get the cis as well. Because there's 2 hydrogens here, both can be removed. However, if stereochemistry is specified, then you might get one over the other. Because sometimes they might specify, they might have like this bromine in the front, the hydrogen in the back, and another hydrogen in the front. The E2 reaction is an anti-elimination reaction, which means that if the bromine's in the front, you need to go for the hydrogen in the back. And in such situation, you have to pick one of these alkenes. But those questions are rare, but keep that in mind though. So if there's two hydrogens, it can rotate, you can get both. But if there's only one available hydrogen, you're going to get one stereoisomer and not both. Now what's going to happen if we use terbutoxide? Dissolved in terbutanol. So because it's a bulky base, it's going to go for the most accessible hydrogen. So we're going to get the Hoffman product. And so the double bond will be on the right side. So we're going to get the less stable Hoffman product as the major product. But now, let's say if we don't have a bromine atom, let's say if we have a fluorine atom. Fluorine is a bad leaving group, but that doesn't mean it can't leave. What do you think the product for this reaction will be? It turns out that even though we have a non-bulky base, we're going to get the Hoffman product. And it's not because of the base, it's because of the leaving group. When you have a bad leaving group, one that doesn't want to leave immediately, so as methoxide goes for the yellow hydrogen, we're going to get a buildup of partial negative charge. The reason why that occurs is because fluorine is a poor leaving group. It takes its time to leave. So as we get this buildup of negative charge, the transition state resembles more like a carbanion rather than an alkene. And so we're going to get the less stable Hoffman product. Think about this. Secondary carbocations are more stable than primary carbocations. And so the reverse is true for carbanions. Primary carbanions are more stable than secondary carbanions. So that's why it's better for the base to grab the yellow hydrogen rather than the blue hydrogen, because as it grabs the yellow hydrogen, we get a primary partially negative carbanion intermediate. Here, if it grabbed the blue hydrogen, we would get like a secondary carbanion, which is less stable. So that's why it goes for the yellow hydrogen, because it forms a more stable carbanion-like transition state. So now let's say if you have a chlorocyclohexane, but in a chair conformation. What do you think the products will be for the following reactions? So once again, we have a secondary alkyl halide, and the chlorine is in the axial position. If we use methanol, we can get a mixture of SN1 and E1. Now, we know that the S1 reaction will give us a racemic mixture. And so the group that we're going to add will be an OCH3 group. This is the inverted product because we went from axial to equatorial. And the other product will look like this, with the OCH3 on the axial position. So that's the retention product. Now, for the E1 reaction, we know we're going to get a double bond. And there's only one place to put it, so we can draw it like this. So that's the E1 product for the first reaction. Now for the second reaction, when we add sodium cyanide and in polar aprotic solvent, this is going to favor an SN2 reaction. So we're only going to get inversion, which means the cyanide that we're going to add, or we're going to replace with the Cl, is going to be in the equatorial position. Because the chlorine was in the axial position, we have to invert it. We have to invert the nucleophile that's coming in to the equatorial position. So we only get this product for we only get this product with sodium cyanide. Now sometimes you might see the reaction in the form of a Fischer projection. So what do you think the products for the following reactions will be? Feel free to pause the video and try the problem yourself. So with ethanol, we know that's a polar protic solvent, and we have a secondary alkyl halide. The carbon that's attached to the bromine is attached to two other carbon atoms. So for an S1 reaction, we're going to get a racemic mixture. So to draw the product, we're going to take off the hydrogen and write what remains backwards. So it's going to be OCH2CH3. So as we can see, this is the retention product because we didn't flip the chiral center. To draw the inverted product, it's going to look like this. We just have to put the nucleophile on the left side. So here, the nucleophile is on the right side. So it's the same as the bromine, so that's the retention. And here it's on the left side, that's the inverted product. Now, SH- is a very good nucleophile, and the crown ether is a polar aprotic solvent. In the presence of a secondary alkyl halide, this is going to favor the SN2 reaction. Now, in an SN2 reaction, we only get inversion. So the nucleophile that we added is not going to be on the right side, it's going to be on the left side. So here it is. This is the product that we get. So what do you think is going to happen if we add sodium hydroxide with water? We have a secondary alkyl halide, so it's going to favor the E2 reaction. Now, when stereochemistry is specified, you have to be careful. So look at all the hydrogens that you can abstract. Here, the hydrogen's in the back because the methyl's in the front. And here, there's two hydrogens, but I'm going to change the color. So because there's two hydrogens, one is in the back and the other is in the front. Now, for the E2 reaction, you can only remove a hydrogen that's opposite or anti to the bromine atom. Because the bromine atom is in the front, we can only remove a hydrogen that's in the back. So we have two choices. We can remove the blue hydrogen or the red hydrogen. So sodium hydroxide is going to pick the hydrogen that will lead to the more stable Zaitsev product. And so it's going to go for the blue hydrogen. And so we're going to get this alkane. Notice that once you put a double bond, this is no longer a chiral center, so we don't have to put the methyl in the front or in the back. So now, let's say if the methyl was in the back instead of the front. And we're going to keep the bromine atom in the front. So how does that change our answer? So that means the hydrogen's in the front now, but we still have two hydrogens on this carbon. So because the bromine's in the front, we can only remove a hydrogen that's in the back. So we have to go for the red hydrogen. So this time, due to stereochemical limitations, we can't get the Zaitsev product. We're going to get the Hoffman product, even with a non-bulky base. So the double bond is over here. Now the methyl group retains its stereochemistry because this is still a chiral center. So this is the product. So now what's going to happen if we have this particular alkyl halide and we're going to use water? So we have a secondary alkyl halide and we have a polar protic solvent, so it's going to favor the SN1 and the E1 reaction. Now notice that the carbon with the bromine is adjacent to a tertiary carbon. So what that means is that rearrangement will occur. So in the first step, the leaving group is going to leave, and we're going to get a carbocation. And since it's adjacent to a tertiary carbon, we're going to get a hydride shift as opposed to a methyl shift. So after the carbocation rearranges, we can get the SN1 or the E1 product. If we get the SN1 product, the water is going to act as a nucleophile attacking the carbocation. Now, we're not going to get a racemic mixture. We're only going to get one product. The reason for that is because the carbon that is attached to the OH is not chiral. It has two methyl groups. So there's no point in putting the OH in the front and in the back. We just get one isomer in this case. Now, for the E1 reaction, water will go for the hydrogen. It's going to act as a base. And then we can get a double bond. So for the E1 product, we can get a mixture of alkenes. We can put the double bond here, or we can put it here. Now, if we place it in the other position on top, you need to realize that these two are identical because these methyl groups are identical. So therefore, you really only get two products as opposed to one. Now, there's no E and Z isomers for this double bond because of these two similar methyl groups. So there's only two isomers that we get, this compound and this one. So two products. So let's start with 3-bromo-2,2-dimethyl butane. So we're going to add sodium iodide to it in HMPA, a polar protic solvent. So since we have a polar aprotic solvent and a secondary alkyl halide, this is going to favor the SN2 reaction. And so there's going to be no rearrangements. And to draw the major product, simply replace the bromine atom with an iodine, but make sure you show inversion of configuration. Now, what's going to happen if we add methanol? So, methanol is going to favor an SN1/E1 reaction. So the first thing that's going to happen, the leaving group is going to leave. Now, notice that we have a secondary carbocation that's adjacent to a quaternary carbon. So we're going to have a methyl shift in this particular example. Now, once we have this carbocation, after it rearranges, now we can get the SN1 and the E1 product. To get the SN1 product, the alcohol is going to attack the carbocation. And after deprotonation, we're going to get this product. And since this carbon is not chiral, we're just going to get one stereoisomer. Now we can also, the methanol can also go for an hydrogen. If it chooses to act as a base, grabbing the hydrogen, it could form a double bond. And so we can get a tetrasubstituted alkene. We can also abstract this hydrogen here and get a disubstituted alkene. So if the problem asks for the major E1 or a major elimination product, it's going to be this one. This alkene has 4 R groups since there's no hydrogens attached to the double bond. Here we have 2 hydrogens, so there has to be at least 2 different R groups. So that's a disubstituted alkene. So this is the major elimination product, and here this is the major substitution product. Now, starting with the same reagent, what's going to happen if we add sodium hydroxide in water? Now, whenever you have a secondary alkyl halide and a strong base, it's going to favor an E2 reaction. Now, in this case, there's no way we can get the Zaitsev product because there's no hydrogens on the quaternary carbon. So we can only get the Hoffman product, so to speak. So hydroxide has no choice but to remove this hydrogen. So we're going to get a terminal alkene. So now let's move on from substitution and elimination reactions into alcohols. Well, I guess we'll still be dealing with such reactions here as well, but this is like a different chapter. So what's going to happen if you add HBr to a secondary alcohol? Is the mechanism going to be SN1, SN2? What would you say? Well, the first thing that's going to happen is if you add HBr to an alcohol, if you wanted to know what the end product is going to be, replace the OH with a bromine group. This reaction is going to be an SN1 reaction, and therefore, tertiary alcohols are more reactive than secondary alcohols, which are more reactive than primary alcohols, in reference to an SN1 reaction. So in the first step, the alcohol is going to grab a hydrogen, and when that happens, it turns into a good leaving group. So the first step is protonation whenever you have acidic conditions, and then water leaves. So now we have a secondary carbocation. There's no tertiary or quaternary carbons next to it, so we're not going to have any rearrangements. So now bromide is going to attack the carbocation. Now, it can attack it from both sides. So since it's an SN1 reaction, we're going to get a racemic mixture. The bromine could be in the front, or it can be in the back. Now, by the way, let's say if the alcohol was primary, and if we add HBr to it. Primary substrates are not very good for an SN1 reaction. So what we're going to get is, for the most part, an SN2 reaction. So this alcohol will grab a hydrogen and expel the bromine atom. So just like before, we're going to turn the OH into a good leaving group. So water is a good leaving group, but the OH is a bad leaving group. So since it's going to be an SN2 reaction, the bromide ion is going to attack the carbon from the back, expelling water. So as you can see, the mechanism is a little bit different, but the end result is the same. You're going to get an alkyl halide. Now, since this carbon is not chiral, it has two hydrogens, we don't have to concern ourselves with stereochemistry. So HCl works the same way, and HI as well. So now let's go back to our secondary alcohol. What's going to happen if we add PBr3? Now, this reaction works by means of an SN2 mechanism. So the end result is that you're going to replace an OH with a bromine atom, but with inversion of stereochemistry. Now, let's say if we were to add SOCl2, thionyl chloride, it's going to replace the OH with a Cl instead, but also with inversion of stereochemistry. So these are SN2 reactions. These reactions, they only work with methyl, primary, and secondary alcohols. They don't work well with tertiary alcohols. What's going to happen to an alcohol if you add sulfuric acid with heat? So this is an acid-catalyzed dehydration reaction, and in the presence of heat, you can drive away water. This is going to be an E1 reaction. The end result is that you get an alkene, the most substituted alkene. So you can get a mixture of products. You can get the double bond could form on the right side of the OH. It could form on the left. We can get the cis alkene, but the major product is going to be the trans alkene. It's the most stable one. By the way, if you see concentrated phosphoric acid or sulfuric acid, both of these would lead to the same product, that is the E1 elimination reaction. But here it's different though. Notice that we have a secondary alcohol next to a tertiary carbon. When you see that, this indicates that we may have a rearrangement. So in the first step, we need to protonate the alcohol. We need to turn it into a good leaving group. In the next step, water leaves, and it leaves behind a secondary carbocation, after which we're going to get a hydride shift, and so now we have a tertiary carbocation. So the hydrogen's now on this carbon. So now we're focused on the E1 reaction. So at this point, let me draw this better. We need to know what base we can use. Typically, when you have concentrated sulfuric acid, there's some water dissolved in it. So we can use water as the base, or we can use HSO4- as the base. But sulfuric acid is a strong acid, so this is really not a good base, so we're going to use water. Now, to get the most stable alkene, we need to get rid of or abstract the blue hydrogen. If we do that, we can get a tetra-substituted alkene, which will be the major product. Now, we can form other alkenes anywhere around that carbocation. So we can put a double bond here and to the right as well. So as you can see, we can get a mixture of alkenes. And but this one, the tetra-substituted one, is the major product. But sometimes you got to find out how many products they can be. Because sometimes they'll say how many different stereoisomers can you get in this reaction. So you got to look for E and Z isomers. This alkene has no E and Z isomers because on one side of the double bond we have two similar groups. Same is true for the major product. On the left side of the double bond we have two methyl groups. However, for this one, all four groups are different. Well, not all four, but on this side, on the right side, we have a hydrogen and methyl. They're different from each other. On the left side, we have an isopropyl and a methyl, which are different from each other. So right now, what we have is the, let's see. So this group has high priority, and this one too. So we have the E isomer. If we want to draw the Z isomer, I'm going to flip the red hydrogen and the methyl. So it's going to look like this. So this is the Z isomer. So we get four different stereoisomers for the E1 reaction. By the way, if you have an alkene, and if you add, let's say, just sulfuric acid to it, especially if it's concentrated sulfuric acid with heat, you can also get this product. So once you have a carbocation, the bisulfate group can now attack the carbocation. The hydrogen's on the other carbon. So sometimes you can add sulfuric acid to a double bond. But if you add boiling water, it can go back into an alcohol. So let's say if we heat it up in boiling water, this is going to ionize. And so you're going to get a carbocation. And you're going to regenerate HSO4-. At which point water will react with the carbocation. And you could get an alcohol. So that reaction is known as a desulfonation reaction. So it's really dependent on concentration. So if you use concentrated sulfuric acid across a double bond, you can get the sulfonic acid group. And then if you add water by decreasing the concentration of sulfuric acid, the water could replace it and you can get an alcohol. So that's something else to know. So now let's move on to a different topic. So let's talk about the oxidation of alcohols. So let's say well actually before we start with this one, let's start with methanol. If we add PCC to methanol, what's going to happen? PCC is very good in making aldehydes and ketones. So PCC will oxidize methanol to formaldehyde. If we use chromic acid, which is a strong oxidizing agent, it can fully oxidize methanol to carbon dioxide. So now, let's say if we have a primary alcohol. If we add PCC to it, we're going to get an aldehyde. If we add a strong oxidizing agent like sodium dichromate with sulfuric acid, this will give us a carboxylic acid. So now let's say if we have a secondary alcohol. If we add PCC, we're going to get a ketone. If we add, let's say, the Jones reagent, chromium trioxide with sulfuric acid or sometimes hydrochloric acid, we're also going to get a ketone. And tertiary alcohols, they're very difficult to oxidize. So for all practical purposes, on the exam, if you have an oxidizing agent on a tertiary alcohol, all you need to say is no reaction. So for the most part, tertiary alcohols are very difficult to oxidize. So now let's say if we have cyclohexanone, what's going to happen if you add sodium borohydride to it, followed by water? Sodium borohydride is a reducing agent, and the boron has 4 hydride ions, and one of them will attack the carbonyl group, and you're going to you're going to get an alkoxide ion. And here's the hydrogen that was added. So in the next step, once you add water, it's going to grab a hydrogen from water. And then so you get an alcohol at the end. Sodium borohydride is very useful for reducing ketones and alcohols. Ketones and aldehydes, not alcohols. It makes alcohols. So here's an example problem. Let's say if you have these 3 functional groups. What's going to happen if you add sodium borohydride to it? So in this structure, NABH4 can reduce the aldehyde, the ketone, but not the ester. So the aldehyde will be reduced to an alcohol. The ketone will be reduced to a secondary alcohol, and the ester will be unaffected by NABH4. So, in contrast, let's say if we use a more stronger reducing agent. Let's use lithium aluminum hydride. Lithium aluminum hydride will reduce everything to an alcohol. It would reduce the aldehyde, the ketone, and the ester. Now, once you reduce the ester, this bond is going to break. And whatever this group is, add a hydrogen to it. So the side product is going to be methanol. So let's work on some examples. Go ahead and predict the products for the following reactions. So in the first example, lithium aluminum hydride is going to reduce the ester to an alcohol. So this bond is going to break. And so you're going to get an OH. And then for the other part, the right side, simply take this group and add a hydrogen to it. That's how you can quickly get the final answer. For NABH4, just replace the aldehyde with an alcohol. And lithium aluminum hydride use the same technique with an ester. So it's going to cleave here. And the carbonyl group, reduce it into an OH. And the leaving group, add a hydrogen to it. So it's going to turn into H2O. That's going to be the side product. So now let's go over the mechanism for the reduction of an ester with lithium aluminum hydride. So the aluminum hydride ion is very similar to sodium borohydride, but it's just stronger. The hydride ion is going to attack the carbonyl carbon, and then you're going to get a tetrahedral intermediate. So here's the hydrogen that we added. Now this is not going to grab a hydrogen, this oxygen with a negative charge. Instead, it's going to use one of its lone pairs to regenerate the carbonyl group, expelling methoxide. So what we now have is an aldehyde. Now, the aluminum hydride ion doesn't stop there. Another hydride ion attacks the aldehyde group, and so we get an oxygen with a negative charge and two hydrogens. So we still have the positive lithium ion, so we can pair it up with the oxygen with the negative charge. And we also have methoxide somewhere, which we can pair it with another lithium ion as well, since we used two of these. So after you add lithium aluminum hydride, usually the second step is water. Now I probably didn't write that, but the second step is always water, regardless if you see it or not. You don't want to mix lithium aluminum hydride with water together, because if you do, they will react. Whenever you have a hydrogen atom bonded to a metal, it usually has a partial negative charge. When hydrogen is bonded to a nonmetal like oxygen, it's partially positive. So this hydride is attracted to this partially positive hydrogen. And so when those two combine, you get hydrogen gas. And as a side product, you'll get this and hydroxide. So you don't want to combine those two together, because lithium aluminum hydride will react with water. So now going back to the reaction that we were talking about, we had an alkoxide and we have methoxide. Once we add H3O plus or water, let's use H3O plus, we're going to protonate all of the oxygens with a negative charge. So this oxygen is going to grab a hydrogen, and it's going to turn into an alcohol, generating water. And the same is true for methoxide. It's going to react with the hydronium ion, and it's going to convert to methanol. So we get these two alcohols when we use lithium aluminum hydride. So what is the product of this reaction? Feel free to take a minute and try this example yourself. So lithium aluminum hydride will reduce everything. It will reduce the carboxylic acid to an alcohol and the ketone into a secondary alcohol. And the side product will be water. Now let's say if you have this reagent or that reactant, what reagent do you need to make this particular compound? So how can you reduce the ester without reducing the ketone? Okay, so if we were to use sodium borohydride at this point, it will reduce the ketone to an alcohol, but it will not reduce the ester. So we can't use sodium borohydride because we want to reduce the ester to an alcohol. So that's not going to work. If we use lithium aluminum hydride, it will reduce both the ketone and the ester. Now we need something that can reduce the ester, so we want to use lithium aluminum hydride, but we need to protect the ketone. So how can we do that? Well, if you wish to protect the ketone from being reduced, you need to make an acetal bond. So there's something called ethylene glycol, which is a 1,2-diol, and it's going to react with the ketone. Ketones are more electrophilic than esters, so the ethylene glycol will selectively react with the ketone. And then you're going to get this protecting group, which looks like this. I'm sure that you've seen this before. So now you can reduce the ester with lithium aluminum hydride. Sometimes you might see this as LAH, by the way. So we're going to get methanol as a side product, but we're not going to worry about that. Now, once you reduce the ester to an alcohol, you can now add H3O+. Once you add H3O+, it's going to react with the acetal group, and it's going to convert it back into a ketone. So it's going to remove the protectant group. What do you think the major product will be for this reaction? Let's say in step 1 we're going to use sodium hydroxide, and in step 2 we're going to use methyl bromide. What's the product for this reaction? Now this is the Williamson's ether synthesis reaction, and in this reaction we're going to use a base to get rid of or remove the hydrogen in phenol. Now phenol is relatively acidic. For most alcohols the pK is around 16, 17, but phenol is around 10, so hydroxide is strong enough to remove the acidic hydrogen on phenol. So we're going to get a phenoxide ion, which is a relatively good nucleophile. And if we add it to methyl bromide, we're going to get an SN2 reaction. The nucleophile is going to attack the methyl and expel the bromine atom. So for the Williamson ether synthesis reaction, you want to make sure that you use only methyl and primary halides, because if you use secondary alkyl halides, you could get an E2 reaction, which won't give you the ether that you want. So now let's say if we don't have phenol. Let's say if we have cyclohexanol instead. So sodium hydroxide is not the best base to remove the hydrogen here. The yield won't be that great. So we need a stronger base. We can use sodium hydride or even sodium metal to get this working. So let's use hydride. Now sodium hydride, the hydride ion has a negative charge, and it's going to be attracted to this partially positive hydrogen, and so hydrogen gas will be created. But we have our secondary alkoxide ion, so I'm going to put H2 as a product, so it escapes as a gas. And then this alkoxide will react with the alkyl halide, giving us an ether. So that's our product. So now let's say if you're starting with an epoxide. What's going to happen if you add methoxide and methanol? Now you need to know where the methoxide is going to go. Is it going to attack the secondary carbon or the tertiary carbon? And what's the stereochemistry as a result? Under basic conditions, whenever you want to open an epoxide ring, the nucleophile is going to attack the less substituted carbon, in this case the secondary carbon. So it goes here, and then this bond breaks. Because it attacks from the back, we're going to get inversion of configuration at the secondary carbon. So at the tertiary carbon, nothing's happening there, so the CH3 is going to stay on the wedge, and we're going to kick out the oxygen, so it's going to be on the dash. it was already on the dash, so since this bond didn't break, it should remain the same. But now, we do have a hydrogen here. So I'm going to draw the hydrogen, and it's in the front since the oxygen is in the back. Now, after methoxide attacks the secondary carbon, the hydrogen is going to flip to the back, whereas the methoxide is going to be in the front now. So if you notice, these two oxygen atoms, they're anti with respect to each other. They're opposite. Now, once the oxygen gets, once we break the epoxide bond, this oxygen will grab a hydrogen from methanol. And so our final answer will look like this. We don't have to show the hydrogen anymore, but we do need to show the methyl group, the OH that was formed, and the OCH3 group. So that's the product of this reaction. So now, let's say if we have the same epoxide, but this time we're going to add methanol under using acidic conditions instead. So in the first step, the oxygen is going to grab a hydrogen. And so it now has a plus charge. Now keep in mind, this bond can open, and if it opens, we can get a tertiary carbocation as a resonance structure. However, putting a plus charge on the oxygen is better, so we're not going to draw the resonance structure. The resonance hybrid looks more like this resonance structure than the other one. But it's good to know that you can get a resonance structure, because that tells you that this carbon has a significant amount of partial positive charge. And so methanol is going to do something strange. It's going to attack from the back of a tertiary carbon, which it appears like an SN2 reaction, but it's not purely SN2. But like an SN2 reaction, we do get that inversion of configuration. However, like an SN2 reaction, but like an SN1 reaction, we're going to add it to the tertiary carbon. So this reaction is like partially SN1, partially SN2. It's like SN2 in the sense that we get inversion, but it's like SN1 in the sense that it attacks the tertiary carbon. So this bond was unaffected. So here we're going to have an OH in the back. Now, because methanol attacked from the back, we're going to have inversion of configuration at this carbon. So the methyl group, which was in the front, it's not going to be in the front anymore. It's going to flip to the back. But the alcohol that we added is now in the front. So notice that it's opposite to the OH group. Now, in the last step, another methanol molecule is going to get rid of this hydrogen. So this is going to be our answer. So we have the alcohol in the back and the OCH3 group in the front. So these two will always be like anti with respect to each other. The OCH3 group and the OH group. And the other methyl group is in the back. Okay, test your knowledge. Try this one. So let's say if we have the CH3 in the front and the oxygen, the epoxide, in the back. But this time we're going to use a different reagent. We're going to use lithium aluminum hydride, but with a deuterium atom instead. So what do you think is going to happen? Well, so here we have Al with the 4 deuterium atoms. And usually, lithium aluminum hydride occurs under basic conditions. If you add it with an acid, it's going to react with the acid and create hydrogen gas. So it's going to act as a nucleophile. So it's going to go for the less substituted secondary carbon. And there's a hydrogen here that's in the front. So let me show that at this point. So when it attacks the carbon, this bond is going to break. So on the tertiary carbon, the methyl will retain its stereochemistry because the reaction did not occur at the tertiary carbon. And the oxygen, which is currently at the tertiary carbon, will also retain its stereochemistry. Now at the secondary carbon, everything is going to change. The hydrogen in red, which is in the front, is going to be in the back now. And the deuterium atom that we added is now in place of the hydrogen, so it's in the front. So as you can see, the stereochemistry at the secondary carbon was reversed, in the sense that hydrogen is now in a new position. So once we add a H2O at this point, this oxygen can grab a hydrogen from water, expelling hydroxide. By the way, if we added D2O, we would be adding a deuterium atom instead. But let's not worry about that. So the methyl is in the front, the alcohol is in the back, deuterium is in the front, and hydrogen is in the back. So this will be our product. So let's say if we have tert-butyl isopropyl ether, and we're going to add HBr to it. Now, ethers are unreactive toward bases, but they do react towards acids, and they're going to cleave. So usually when you add a 1-to-1 ratio of an ether and an acid, you're going to get an alcohol and an alkyl halide. The question is the OH going to go on the tertiary carbon or on the secondary carbon? Now, if you have a tertiary carbon, typically this reaction works by means of an SN1 mechanism. In the first step, the oxygen grabs a hydrogen, and the bromine will leave. And at this point, one of the bonds is going to break. It's going to break in such a way that you get the most stable carbocation. In this case, we want to get the tertiary carbocation. So we're going to break it that way. If we broke it this way, we would get a secondary carbocation, which is less stable, so that's not going to happen. The tertiary carbocation will form faster. So here we have isopropyl alcohol. Now the bromide ion is going to attack the tertiary carbon. So this time we're going to add the Br on the tertiary alkyl halide when it favors an SN1 mechanism. Sometimes it can favor an SN2 mechanisms. So let's say if we don't have any bulky groups. So let's say if we have this and we added HBr. So the first step is going to be protonation. Right now the oxygen is not a good leaving group. So now after protonation we need to decide what's going to happen. In the last example, the bromine went on the most substituted carbon, that was the tertiary carbon. But here, is that going to be the case? So if it's SN1, the bromine goes on the most substituted carbon. If it's an SN2 mechanism, it's going to go on the least. And it's very difficult to form a methyl or primary carbocation. They're not stable. So if you have a primary and a methyl group, it's going to favor the SN2 reaction. And so bromide is going to behave as a nucleophile. And it's going to attack the methyl carbon because it's less hindered. So when it attacks the methyl carbon, this bond is going to break. So whenever you have an SN2 reaction, the bromide attacks the less substituted carbon. So we get methyl bromide and ethanol. That reaction is also reversible too. The alcohol could react with methyl bromide, giving you the ether again. So it really depends on, how much HBr you add to it. By the way, if you add excess HBr, you can drive this reaction all the way to the right. In this case, you're going to put a bromine atom on both alcohols. On both carbons, the tertiary and the secondary carbon. In the first step, you're going to get a tertiary alcohol. I mean, not a tertiary alcohol, excuse me. I take that back. In the first step, you're going to get a tertiary alkyl halide and isopropyl alcohol. Now remember, earlier in this video, we talked about adding HBr to an alcohol. If you had excess HBr, then another HBr could react with this alcohol, and we talked about the mechanism of that reaction. The OH is going to get protonated, it's going to leave as water, then the bromide ion is going to attack the carbocation, and so that's going to convert into isopropyl bromide. So if you add excess HBr, basically you should see no alcohols as your product. This is going to be the answer. You just put a bromine everywhere you can. So let's say if we have this group. If we're going to add excess HBr on both sides, you can cleave it here and cleave it here. Get rid of the oxygen and just put 2 bromine atoms on both sides. So sometimes you might have multiple oxygen atoms. So let's say we added HCl, excess HCl. So cleave it on this side, here, and here. So here we have an ethyl group on the left, so we're going to get ethyl bromide. On the right side, we have an isopropyl group, so we're going to get isopropyl bromide. Now, in the middle, we have 3 carbons, and we cleaved it on the left side and on the right side, so we're going to get 2 bromine atoms on carbon 1 and on carbon 3. So this bond, let's review. This bond was cleaved. We put a bromine on that side. This bond here was cleaved, so we put a bromine on this side here. And for the last example, this side was cleaved and this side was cleaved, so we put 2 bromine atoms on those 2 sides. So now let's say if we added HCl to this particular ether. What's going to happen? Now, we're not adding excess HCl, we're just adding regular 1 equivalent HCl. Whenever a phenyl ring is attached directly to the oxygen, you're always going to get phenol as your answer. It's very, very difficult to kick off the OH with a Br. It's just not going to happen. For all practical purposes, even if you use excess HCl, the phenol will remain. So the chlorine will go on the other side, and that is the ethyl group. So to discuss the mechanism, this oxygen is going to grab a hydrogen, just like before. And then it converts into a good leaving group. So here we have a secondary carbon and a primary carbon. This is an arrow group, so SN1 or SN2 reactions will not work there. So this bond is not breaking. It's just not going to happen. So we need to decide if it's going to be an SN1 or SN2. So the chloride has to react somewhere over here. For it to be an SN1, the bond will have to break this way, and we would get a primary carbocation, which is not stable. So SN2 is the best mechanism for this problem, because SN2 reactions work well with primary structures. So the chloride is going to attack the primary carbon, and that bond is going to break. So we're going to get phenol. And ethyl chloride. So now let's say if we start with cyclohexanone, and let's add a Grignard reagent to it. So in the first step, we're going to add methyl magnesium bromide. And in the second step, we're going to add H3O+. What's going to happen here? Feel free to pause the video and see if you can get the major product. So the methyl group has a partial negative charge, and it's going to attack the carbon no carbon. And so once we add the R group, the double bond O is going to break, and it's going to become a single bond O. but it's going to have a negative charge. And so we have this. And then in the last step, the oxygen is going to grab a hydrogen from H3O plus. And so it turns into an alcohol. And so what we get is a tertiary alcohol. So that's what happens when you add a Grignard reagent to a ketone. You get a tertiary alcohol. So if you can keep that in mind, you can quickly look for the product if you have a multiple choice test. By the way, if you're taking Orgo 2, I'm going to post a link to this video where you can take an Orgo, a 100 practice problem multiple choice test. This is for Orgo 2 students, by the way. I haven't created one yet for Orgo 1, but in time I'll do that too. Try this one. What do you think the major product is for this reaction? So here, the methyl group is going to attack the carbonyl group. The organolithium reagent works very similar to the Grignard reagent. As you can see, the mechanism is almost identical. And for these reactions, it's good to understand the mechanism because the answers can vary a lot. So now, in the last step is protonation. We need to grab a hydrogen. By the way, what solvents is best to use? What solvents should we use in connection with a Grignard or an organolithium reagent? What do you think? The solvents that don't react with Grignard or organolithium reagents are ethers. So if you see that on a test, make sure you pick an ether. One of the most common ethers you can use as a solvent is diethyl ether, which looks like this. By the way, this answer can also be written this way, ethanol. So when you add an organolithium reagent or even a Grignard reagent to formaldehyde, you're going to get a primary alcohol. So notice that we can only add one R group to a ketone or an aldehyde. But now let's say if we have an acid chloride or even an ester. How many R groups will the Grignard reagent add to it? What do you say? In the second step, we'll add H3O plus later. So in the first step, the methyl group is going to attack the carbonyl carbon. So we're going to add the CH3 in the first step. And notice that we have this leaving group. With an aldehyde or a ketone, we didn't have that Cl. So after that, we have to protonate the oxygen. But here, because we have a leaving group, we're not going to protonate the oxygen yet. Instead, what the oxygen is going to do is going to reform double bond O, and then it's going to expel the leaving group. So the acid chloride gets reduced to a ketone once we add the first R group. But now the Grignard reagent doesn't stop here. It will reduce the ketone further into an alcohol. So this is when we're going to add the second R group. So it attacks again, add another methyl group. And so now we have an oxygen with a negative charge. So now there's no more leaving groups to kick out. So at this point we need to add H3O plus. And so it grabs the hydrogen and we get water as a byproduct. So here once again we have a tertiary alcohol. And these are the two methyl groups that we added. I've labeled it in green. So anytime you add a Grignard reagent or an organolithium reagent to an acid chloride, it will be reduced to a tertiary alcohol. The same is true if you add it to a ketone, you get a tertiary alcohol. But now what happens if we add a Gilman reagent, which is written this way? You might have seen this before. R2 copper lithium. What's going to happen? Now, the Gilman reagent is a weaker version of the Grignard reagent. In this structure, copper has a negative formal charge, lithium has a positive formal charge. So the methyl group attacks the acid chloride. So you get this structure, and we're going to add one R group. The difference between the Gilman reagent and the Grignard reagent is that the Gilman reagent adds only one R group to an acid chloride. The Grignard reagent adds two. So the Gilman reagent stops at the ketone level. So make sure you remember that on the test. The Gilman reagent converts the acid chlorides into ketones, not alcohols, whereas the Grignard and the organolithium reagent will reduce it all the way to an alcohol. So we're going to stop here at the Gilman reagent. It doesn't reduce a ketone. So make sure, if you can remember that for your test, on a multiple choice test, you can quickly identify the answer. Now, another one you want to know is DIBA. Now, you might have seen it as DIBA. Sometimes some tests may not show it to you as DIBA. But if you see this reagent will reduce an acid chloride and stop at the aldehyde level. It's very similar to lithium aluminum hydride, but instead, if you notice, there's only one H, one hydrogen attached to the aluminum atom. So if you draw it out, there's like 3 OR groups attached to aluminum, but only one hydrogen. So aluminum will not, this aluminum hydride reagent, it won't completely reduce it to an alcohol. So it's going to stop at the aldehyde level. It can only add one hydrogen to it. Now, as you can see, the mechanism for these reactions, they're very similar. Now, once we add this reagent, the oxygen's going to form a carbonyl group, and it's going to expel the leaving group. So here, we're going to stop at the aldehyde level. So make sure you know that for the test. DIBA, it makes aldehydes. So now, what's going to happen if we add lithium aluminum hydride to an acid chloride? What are we going to get? So here, there's 4 hydrogens on the aluminum atom. So this is going to be reduced all the way to the alcohol level, which means we need to add 2 R groups. It just so happens that the R groups are hydrogens. So once we add the first hydrogen, we know what's going to happen next. We're going to regenerate the carbonyl and expel the leaving group. So now we have an aldehyde. But it doesn't stop here. Another aluminum hydride ion attacks the aldehyde. We could use a new AlH4 molecule. We don't have to use the other one that we use. So now, we have 2 hydrogens that we added. So at this point, there's no chlorine groups to kick out. So the last step is protonation by H3O+. And make sure that's in the second step. It can be H2O or H3O+. So now this oxygen is going to grab a hydrogen, and we're going to get water. So our final answer here is a primary alcohol with the addition of 2 hydrogens. So let's review. From an acid chloride, if you add a Grignard reagent or an organolithium reagent, you're going to get a tertiary alcohol. If you add DIBA, it's going to turn into an aldehyde. If you add the Gilman reagent, which is the R2 copper lithium, it's also known as lithium, like an organocopper lithium reagent, that's going to give you a ketone. And if you add lithium aluminum hydride, you're going to get a primary alcohol. If you want a secondary alcohol, you need to start with an aldehyde and add a Grignard to it. But you don't want to start with formaldehyde where you have 2 hydrogens. You want to start with an aldehyde where you have one hydrogen and an R group. And then following protonation, you get a secondary alcohol. So now, let's say if we have an ester, but inside a ring, because sometimes you'll see that on an exam. What's going to happen if we add an organolithium reagent? For this, I would just do the mechanism. So the methyl is going to attack the carbonyl carbon. Now you need to know that the ring is going to open. So here's the methyl group. In the next step, the oxygen is going to form a double bond and expel the other oxygen. So on one side, we have a ketone, and on the other side, we have an oxygen with a negative charge. So now, the organolithium reagent, which reacts just like a Grignard reagent, won't stop there. It's going to react with the ketone as well. So now we have the addition of two R groups. And we still have the oxygen with a negative charge. So we have two lithium ions paired up to both oxygens. So now, in the last step, we're going to add H3O+. So all we need to do is add an OH to each oxygen. So here we added two R groups, as we can see. But let's convert this into a line structure. And this should be an OH. So let's call this carbon 1, 2, 3, 4, 5. We can count it the other way, but we're not trying to name it. We just want to know how to draw it like this. So on carbon 1, we have an OH group. And on carbon 4, we have an alcohol and a methyl. So the answer should look something like this. You should have two alcohols when you add a Grignard reagent to a cyclic ester. A cyclic ester is also known as a lactone. So now, what happens if we add a cyclic ester to a Gilman reagent? A lithium dialkyl cuprate reagent. So remember, the Gilman reagent will convert an acid chloride to a ketone. It's going to do the same thing to a cyclic ester. So in the first step, we're going to have a methyl group that is going to attack the carbonyl carbon. And then this is going to break. We're going to kick off the oxygen. And so here we have a ketone. And here we have an oxygen with a negative charge. So once we add H3O+, it's just going to open. Well, it's going to grab a hydrogen. And it stops here. So as you can see, it stops at the ketone level. And with the ester, you're always going to get this side product, this alcohol. So now let's say if we were to use dibol. So here we have an aluminum with one hydrogen and three OR groups. So this is going to attack here. Now remember, dibol, it makes aldehydes. Now this is going to open. It's going to kick out the oxygen. So as you can see, we have an aldehyde here. But the side product will always be an alcohol. So after we add H3O+, this is going to grab a hydrogen. So in the end, we're going to get an OH plus an aldehyde. So now what if we add lithium aluminum hydride but with deuterium instead? What's going to be the major product? So one of the deuterium atoms is going to attack the the carbonyl group. So here it is right now. And then we know this is going to reform into a carbonyl group, expelling the oxygen. And then another one will attack the aldehyde. And so now we have two deuterium atoms. Then in the last step, we're going to add H3O+. So we're going to get an alcohol on both sides. But on one side, there's going to be two deuterium atoms. So that's what lithium aluminum hydride would do if it has deuterium on it. So let's review. Let's see if we can quickly draw the major product for the following reactions. So let's say if you have a ketone, and if you want to add this R group in the first step, and in the second step H3O+, what's the final answer? So when you have a ketone, you can only add one R group to it. The ketone will be reduced to an alcohol, and look at the 4 carbons here that you see. So that's going to be the answer. So let's say if we have cyclohexanone with phenolithium, and in the second step H3O+. So the final answer, this is going to be reduced to a tertiary alcohol, and we're just going to add one R group. Sometimes you could write this as pH for phenyl. So now let's say if we have an ester. Actually first an acid chloride. And let's say if we use a Grignard reagent. Phenyl magnesium bromide. Followed by H3O+. So if you add a Grignard to an acid chloride, you can add 2 R groups. The acid chloride will eventually be reduced to an alcohol, and we're going to add 2 phenyl groups, which you can draw it as a benzene. So now let's say if we have an acid chloride and an organolithium reagent. Let's use this compound. What do you think the major product will be? So the acid chloride will be reduced to an alcohol, and then simply add your 2 R groups. So you're going to get a tertiary alcohol. So now what's going to happen if we start with an acid chloride, and if we add diol to it? So remember, diol, that's when aluminum only has 1 hydrogen. So in this case, the acid chloride gets reduced to an aldehyde. Simply replace the chlorine with a hydrogen, and you're going to get the answer. So now, from the same compound, let's say if we use the Gilman reagent. So instead of going down to the aldehyde level, we're going to get a ketone. So all you need to do is replace the R group, the chlorine, replace the chlorine with the R group. That's what I meant to say. And so here it is. As you can see, we get a ketone. So now let's use an ester. So what's going to happen if we add methyl magnesium bromide to this ester? The reason why I'm giving you so many examples in this topic is because you're going to see a lot of these on the test. You need to know that the ester is going to be reduced to an alcohol, and you need to add the R group twice. So you're going to get a tertiary alcohol. If you add, let's say, propylithium with H3O+ in the second step, convert the ester into an alcohol, and add two R groups, 1 and 2. So here's another ester. Let's say if we add diol to this ester. So it could be written like something like that. The key is if you see one hydrogen on aluminum, you know it's diol. Replace this R group with a hydrogen. So remember, diol makes aldehydes. By the way, this group that leaves, after you add like H2O plus, or if you do add it, eventually it turns into an alcohol. So that's like the side product, in case you're wondering. For the other ester where we had the OCH3, the side product will turn into methanol. Simply add a hydrogen to it if you need to draw the side product. So for our last example, let's use the Gilman reagent. So we're going to replace the leaving group with an R group. In this case, the R group has 4 carbons. And we only need to add one of them. So 1, 2, 3, 4. So here we have a ketone instead. So now let's move on to 1,3-butadiene. So what's going to happen if we add Br2 to it? There's two products that we can get. We can get the 1,2 addition, where there's a bromine on carbon 1 and on carbon 2. And we can get the 1,4 addition, where the bromine's on carbon 1 and 4, with a double bond between 2 and 3. So sometimes you might have more complicated carbon structures around 1,3-butadiene, but if you focus on these 4 carbons, you can always identify where the product is going to be. I'll show you some examples. Now you need to know that the 1,2 addition product is the kinetic product, and the 1,4 is the thermodynamic product. So at low temperature, let's say if it's like -40, you're going to get the kinetic product. At high temperature, let's say if it's above 20, like let's say 60 degrees, the thermodynamic product is going to win. One way to identify the kinetic product is the kinetic product occurs faster because it generates the most stable carbocation intermediate. The bromine that's 1 carbon away from the double bond comes from the carbocation intermediate. So as you can see, this carbon is secondary. Both of these carbons here are primary. So this one came from a secondary carbocation, this came from a primary carbocation. So the kinetic product always comes from the most stable carbocation. The thermodynamic product is associated with the most stable double bond. This double bond is an internal double bond, and so it's di-substituted. It has 2 R groups. Whereas this double bond is a terminal one, and it only has 1 R group, so it's less stable. So the thermodynamic product, it forms, it's the most stable product at high temperature. So let's try another example. Let's see if we can quickly draw the major product. So let's say if we have HBr, and we're going to heat it to 40 degrees Celsius. So this is above room temperature, so we're going to get the thermodynamic product as the major product. So what you want to do is identify the 4 carbons of 1,3-butadiene. Even though this is a different diene, this is like really 2,4-hexadiene, focus on the 1,3-butadiene, those 4 carbons, because that's where we're going to get our answer around those carbons. So on carbon 1, to get the 1,2 product, we're going to put the hydrogen on carbon 1 and the bromine on carbon 2. The element that's partially positive is going to go on carbon 1. The element that's partially negative goes on carbon 2. Now, to draw the thermodynamic product, keep the partially positive hydrogen on carbon 1. That's going to stay. Now, the bromine is going to move from 2 to 4. So we're going to put it here. And a double bond is going to switch places with the bromine. It's going to go between 2 and 3. Remember these rules because they always work out the same way. So this is the 1,2 product. This is the 1,4 product. So since the temperature is above 20 or 25, we're going to get this as our answer, the 1,4 product, the thermodynamic product. If it was at negative 20 or something, then we'll get the kinetic product. But that's how you can quickly draw it. So let's try another example. So let's say if we have another symmetrical system, but this time we're going to add ICl. So iodine is partially positive with respect to chlorine because chlorine is more electronegative. So let's count those 4 carbons. 1, 2, 3, 4. So on carbon 1, we're going to put the element that's partially positive. That's the iodine. And on carbon 2, we're going to put the chlorine. And between 3 and 4, we're going to have the double bond. Now, to draw the other structure, we're going to keep the iodine atom at carbon 1. We're going to put the Cl on carbon 4, and then a double bond between 2 and 3. So now we have our 1,2 product and the 1,4 product. So let's say the temperature is low, like negative 60. So we're going to get the 1,2 product, the kinetic product. Now, let's think about this. Because sometimes the 1,2 is not the kinetic product. It appears to be the kinetic product, but is it? Now remember what we said, the kinetic product is usually the one that goes through the most stable carbocation intermediate. And for this particular example, the 1,2 product is not going to be the kinetic product. This is one of those rare cases. And here's why. Notice where the chlorine is. The chlorine is on a secondary carbocation. But here, in the 1,4 product, it's on a tertiary carbocation. And tertiary carbocations form faster than secondary carbocations. So even though the 1,2 product is usually associated with the kinetic product, in this particular case, the 1,4 product is the kinetic product because it goes through a more stable carbocation intermediate. Now, it turns out that the 1,2 product is actually the thermodynamic product. It's kind of reversed. The reason being is if you have to look at the alkene stability for that. Here, this alkene has 2 R groups. 1, 2. So it's disubstituted. This alkene has 3 R groups. So it's trisubstituted. Usually, the one that gives you the most stable alkene is your thermodynamic product. That's what you get at high temperature. So this really is going to be the answer. So watch out. That was a curveball. Let's talk about the mechanism for that reaction. Because it was unique. So the double bond is going to attack the iodine atom and expel the chlorine atom. So we're going to add the iodine to carbon 1, and on carbon 2 we're going to have a plus charge. So right now this is a secondary carbocation, and it can rearrange. The double bond can move here. So now the double bond is between carbons 2 and 3. So let me just count it. This is carbon 1, 2, 3, and 4. And now attached to carbon 4, we have a carbocation. So now the chloride, it can attack carbon 2 or carbon 4, giving us 2 different products. So as you can see, this compound contains a tertiary carbocation. So it leads to the kinetic product, even though it's 1,4 in this case. This one has the most stable double bond, which is a tri-substituted double bond, so it leads to the thermodynamic product. Now, because this molecule is symmetrical, we get two different products. If we don't have a symmetrical system, we can get up to 4 products. So let's do one example here. So this compound lacks symmetry. So here's what we're going to do. To quickly draw all 4 products, let's count this as carbon 1, 2, 3, 4. There's our butadiene system. And then we're going to count it the other way soon. And then we'll go through the mechanism. So let's use BrCl. So bromine is partially positive with respect to chlorine. So we're going to put bromine on carbon 1 and the Cl on carbon 2 and a double bond between 2 and 3. So this is the 1,2 product, which may or may not be the kinetic product. We'll analyze it later. And to draw the 1,4 product, keep the Br on carbon 1, put the double bond between 2 and 3, and put the Cl on carbon 4. Okay, so those are the first 2 products that we have. So this is the 1,4 product. Now, to get the other 2 products, we're going to count it the other way. So this is going to be carbon 1, 2, 3, and 4. And we're going to follow the same rules. So on carbon 1, we're going to put the bromine atom. And on carbon 2, we're going to put the chlorine. And the double bond is going to go between 3 and 4. So for the other answer, for the 1,4 product, so this is, let me write this as 1,2. The bromine is still going to be on carbon 1. The double bond is going to move between 2 and 3. And the Cl is going to be on carbon 4. So those are the 4 products. Now, in a situation like this, you don't want to say just the 1,2 is the kinetic. It's a little bit more complicated than that. The kinetic product is the one that occurs through the most stable carbocation intermediate. It has that. We need to look for the tertiary carbon. So keep in mind, the element that's partially negative is the one that's going to attack the carbocation. So we got to focus on where the Cl is. In the first example, the chlorine is attached to a secondary carbon. So that means that reaction proceeded through a secondary carbocation intermediate. Here, this is secondary as well. This is secondary, but this one is tertiary. So if the temperature was like negative 80 degrees Celsius, this would be the answer, solely this product, because it's different from the rest. It's the only one that has a tertiary carbon. So this is the kinetic product, which it turns out it's a 1,2 product. But not both 1,2 products were the kinetic product. This is the major kinetic product. Okay, so now let's look for the thermodynamic product. So now we need to analyze the alkene stability. This double bond has 2 R groups. It's attached to 2 carbons. And you don't count the carbons that are part of the double bond system. Here, this alkene has 3 R groups. 1, 2, 3. This one too has 3 R groups. 1, 2, 3. And so this one as well. So all of the other alkenes are tri-substituted, which means at high temperature, all of them can form. They're equally stable. They occur through a secondary carbocation intermediate, and they're all tri-substituted, so they are all the thermodynamic products. So both of these 1,4 products is a thermodynamic, plus this 1,2 is also a thermodynamic product. So now let's briefly go through the mechanism for this reaction. So the alkene attacks the bromine, expels the chlorine. So the bromine is on carbon 1, and we have a carbocation on carbon 2. So here, that's a secondary carbocation. And then we're going to draw the resonance structure. And at this point, the double bond is now between 2 and 3, and the plus charge is on carbon 4. And at this point, the chloride could attack this carbocation, or it can attack this one, leading to 2 different products. So here, we're going to get the 1,2 product. and in the other example, we're going to get the 1,4 product. So that's the mechanism for the first two products. So now let's use the other double bond instead, so we can get the other two products. So now using this alkene is going to attack the bromine atom because it's partially positive, and it's going to expel the chlorine atom. So this double bond remains. We're going to put the bromine atom on carbon 1, and we're going to have a plus charge. And then we're going to draw the resonance structure. So now the double bond is between carbons 2 and 3, and the plus charge is on carbon 4. So at this point, the chloride ion could attack this carbocation or this one, leading to the other two products. So here the chlorine is now on the tertiary carbon, so that's the major kinetic product, but here it's on the secondary carbon. So that's how you can get the other answers. So now let's go over the Diels-Alder reaction. The Diels-Alder reaction is a 4 plus 2 cycloaddition reaction. That's the diene, which we have 2 double bonds. The dienophile is the one that has 1 double bond. Electron donating groups like methyl groups and hydroxy groups and methoxy groups, they cause the diene to be more reactive. Electron withdrawing groups like the nitro group or carboxylic acid, they make the dienophile more reactive. Now this double bond will connect carbons 1 and 6 together. And then this double bond moves here, and then this one connects carbon 4 and 5. So what you're going to get is a 6 carbon ring. So here we have a methyl group on this side, and here this carbon is chiral, so we're going to have a CN group in the front plus 1 in the back. So you actually get a racemic mixture. The CH3 is not chiral because it's attached to a ring and a double bond. So you only have 1 group at this carbon. A total of 3 groups actually. You don't have 4 groups. But here we have a racemic mixture. Now keep in mind though that the dienophile can approach the diene in the opposite direction. So it can approach it like this. So we can get another set of products as well. So now the cyanide is on this carbon, and we can get the enantiomer. We can put the cyanide group in the back as well. So you can get a mixture of products, as you can see. So what do you think is going to happen if we combine this particular diene with this dienophile? Feel free to pause the video and draw the major product. So go ahead and try this one. So you're always going to get a 6 carbon ring. So between carbons 2 and 3, you're always going to get a double bond. On 2 we have a methyl, and on 5 and 6 we have a CF3 group. Now notice that the CF3 groups are trans with respect to each other, so we have to show that. So one of them is going to be in the front and the other is going to be in the back. Plus we'll get the enantiomer. So if we wish to draw the enantiomer, it's going to look like this. We simply have to just reverse the configuration. So that's it for this example. Alright, let's move on to another Diels-Alder example. Try this one. So let's say if we have 1,3-butadiene, and let's say if we have this group. By the way, I do want to mention this. Sometimes they may show you 1,2-butadiene like this. They don't always put it in the S-cis form. You might see it in the S-trans form. And this group, you might see it as CH3, carbonyl O with a triple bond. I messed that up. Hold on, let me fix that. I completely destroyed that structure. Okay, this is supposed to be O. There we go. So it might look like this. So if it's in this form, would you recognize that this is a Diels-Alder reaction? You need to see that you have a diene here, 2 double bonds, and you have a triple bond next to 2 electron withdrawn groups. Because sometimes they don't always put it in a nice form. You have to recognize that this is the Diels-Alder reaction. Once you identify it, redraw it this way, and then you can quickly see what the products will be. So this will be 1, 2, 3, 4, 5, and 6. So draw the 6 carbon ring. Between 2 and 3, you're going to get a double bond. Now, notice that we have a triple bond here. Before, we had a double bond which went down to a single, so the triple is going to go down to a double. And then we can add our 2 groups here. So notice that these 2 carbons are not chiral. So therefore, we don't have to put it on a wedge or on a dash. So go ahead and try this example. So now, do you recognize that that's a Diels-Alder reaction? I know we're on the topic, but how would you draw the major product if it's given to you in this form? So first, identify the 4 carbon atoms of the diene, and then draw your generic diene structure. Now, the additional 2 carbon atoms, view that as a substituent, so we can put it here, 1, 2. Then draw the dienophile, and notice that the 2 electron withdrawn groups are trans with respect to each other. So write it this way. Now once you have it in this form, you can now draw your product. You know you're going to get a 6 carbon ring with a double bond between 2 and 3. And on carbon 4 we have an ethyl group, so we can put it there. And here's the 2 CF3 groups. They're trans with respect to each other. And then we're going to add the enantiomer as well. By the way, this carbon is chiral, so you can put that on a wedge or on a dash. So actually, you might get a mixture of diastereomers, because these 2 might reverse in configuration. That could stay the same. So you might just get diastereomers instead of enantiomers. So now let's say if you have cyclopentadiene. So this time our diene is in a ring. So when you start with a ring, you're still going to get a new ring, so we're going to get a bicyclic compound, a compound with 2 rings. And we're going to draw it 2 different ways. So this is our diene, 1, 2, 3, 4, and here's our dienophile. Most of the time you'll see it in this form. So these are the 6 carbon atoms that we have. That's the new ring that we formed. And we have 2 CF3 groups. They're cis with respect to each other, so we're going to put it like this. This is known as the exo product. Now notice that we have a carbon atom between 1 and 4. Let's call it carbon A. Carbon A, we need to draw it right here. And there's going to be a double bond between 2 and 3. Now there's another product that we can draw too, and that is called the endo product. And that's where the 2 CF3 groups, they're facing in a downward direction. And there's carbon A. So as you can see, we can get 2 possible products, but however, you need to know that the endo product is more stable than the exo product. So the endo product is the major product. On a test, don't pick this one. So now let's say if we have cyclohexadiene. And this time, we're going to have 2 carboxylic acids. I forgot to draw it the other way, but I'm going to do it in this example. So there's 2 carbons here. Let's call it carbon A, carbon B. So here are the 2 carbons. And because we have trans, one is going to be in the exo position, the other is going to be in the endo position. So we can get that plus the enantiomer. Because one is endo and one is exo, these two are equally stable, so you get both products as a result. Now, you can also draw it this way too. Let's say this is our 6 carbon atom system, the new ring that we generated. So here we'll have a COOH in the front and a COOH in the back. Now we still need to show carbons A and B. So those 2 carbons you can draw it like this. So here's carbon A and here's B. So that's another way you can show it as well. So starting with cyclopentadiene, go ahead and draw the major product for the following reaction. So this time we have a triple bond. So let's draw the bicyclic compound like this first. So because we have 1 carbon atom between carbons 1 and 4, there it is, that's carbon A. And the triple will be reduced to a double, and here there's no endo or exo product because the nitro groups are attached to a double bond. This carbon is not chiral, so there's only one way you can draw it. And to draw it the other way, we're going to have our 6 carbon ring, our 2 nitro groups, next to a double bond, and then there's 1 carbon atom here. So that's the other way you can draw it. So what do you think the product will be if you combine these 2 together? Now, when I'm giving you a lot of examples on a certain topic, it's because you're going to be tested on that topic a lot. You'll see a lot of questions on it. So let's identify our 6 carbon system. Now for this, we can draw a bicyclic system if we want. And we have 1 carbon atom between carbons 1 and 4. There's a double bond on carbon 2. And this is like the exo product. If you want to draw the endo product, we have to point it downward. And I'm always running out of space. Now if we want to draw it the other way, it can look like this as well. And there's 1 carbon atom between carbons 1 and 4. So you can draw it that way as well. So what do you think the product for this reaction will be? So notice that you can form an attachment here and here. So if you see this on the test, this is how it's going to look like. And there's going to be a double bond on this side between carbons 2 and 3. And that's the answer for that reaction. Now sometimes you might get a question where you have to determine the diene and the dienophile that makes the product. So if you get a question like that, how can you do it? So feel free to pause the video and try this problem yourself. Actually, you should do that for all examples. When I write out a problem, quickly pause the video and see if you can get the answer. So first, identify your diene. That's these 4 carbons. And make sure that 2 and 3 is between a double bond. It's always going to be like that. So now, the original diene has a double bond between 1 and 4. On carbon 2, we see that we have a methyl. So that's the diene. For the dienophile, between 5 and 6, if we see that we have a single bond, before it was a double. And notice that the CF3 and the COH are trans with respect to each other, so we're going to write it like this. So that's how we can get the original diene and dienophile that made that product. Let's try another example. So here we have the endo product. So let's identify our 4 carbons, and here's 5 and 6. So the first 4 carbon atoms starts from the diene. On carbon 2 we have a methyl group, and on carbon 3 we have a methyl, so that's the original diene. Now you can also see it this way. So you may need to be able to convert it to this structure because on a test it might look like that. Now, actually no, we have to fix that. It's not going to look like that. I take it back. We're still going to have those 2 methyl groups, but I completely forgot about carbon A. So what that means is that this structure was originally in a ring. So we got cyclopentadiene with 2 methyl groups on it. So this is the proper structure. Now for the dienophile, it's a double bond and it has 2 groups. Because they're both endo, that means we had a cis dienophile. So it's going to look like this. This is the answer. So if you have a bicyclic compound, that means usually the diene was in a ring. And if there's 1 carbon here, it's like a cyclopentadiene ring. If there's 2 carbons, cyclohexadiene. Okay, so that's it for the Diels-Alder reaction. I do want to mention one more thing about it, and that's reactivity. The one that's most reactive is the one that's locked in the S-cis conformation. So this is number 1. This is the most reactive. This one in a ring, it's locked in the S-trans form. So this one cannot react in the Diels-Alder reaction. So that's number 4, least reactive. This one is number 2. It's the second most reactive. This one is number 3. It's the third most reactive. In number 2, you can see the methyl groups are far apart. So it's easy for it to adopt the S-cis conformation. And number 3, you can see the methyl groups are clashing. There's a lot of steric strain, so it's very difficult for it to form the S-cis conformation. So these 2 are not very reactive, 3 and 4, but 1 and 2 are reactive, and 1 is very reactive. By the way, the more donating groups that you add to the diene, the more reactive it becomes. So donating groups would be like a methyl, a methoxy group, and OH. These are common donating groups that increase the strength of the diene. For the dienophile, the donating groups are like the electron withdrawing groups are these. These electron withdrawing groups they cause the dienophile to be more reactive. And this is for the diene. Okay, so let's move on to aldehydes and ketones. Reactions at the carbonyl-carbon. So, what's going to happen if we add ethylene glycol with an acid catalyst to cyclopentanol? What do you think the major product will be? Now, what's going to happen is we're going to get a protecting group, which looks like this. So this is an acetal group, and once we add H3O plus, we can remove the group and it converts back into a ketone. So let's say if we have cyclohexanone, but let's say we have a diol that looks like this. How would you draw the protectant group at this point? So once you put your two oxygen atoms, notice that there's 3 carbons between the two oxygen atoms. So you're going to get a structure that looks like this. Now starting from this ketone, what happens if we add HCN? So this reaction is going to form a cyanohydrin. There's the acid catalyzed version, and there's the base catalyzed version. This is the acid catalyzed version, where the ketone grabs the hydrogen from the HCN molecule. And then in the next step, cyanide attacks from the back. And then so you get an alcohol and a cyanide group. Now if you add H3O plus, the nitrile group gets converted into a carboxylic acid. So this is an alpha hydroxy carboxylic acid. By the way, these reactions are known as nucleophilic addition reactions. So now what's going to happen if you add methanol to a ketone? Well, first you're going to get a hemiacetal. Some books might call it a hemiketal, but the word acetal is more common. So you're going to get an OCH3 and an OH group. By the way, these reactions are reversible. Now if you add excess methanol, you're going to get the acetal instead of the hemiacetal. So you get like 2 OR groups. A quick way to identify the acetal, look for the carbon that has 2 oxygen atoms. So here's a typical example that you might see on the exam. So here we have a monosaccharide. I'm not sure which one exactly it is. It could be like glucose, mannose, galactose, one of those sugars. But let's say if we add methanol to it. What's going to happen? Well, for this question, you need to know that the acetal carbon is the one that reacts. So the OH that's attached to the, I take that back, the hemiacetal. Look for the carbon that has 2 oxygen atoms. And here it is. This carbon has 2 oxygen atoms. So here we have an OR and an OH, so that's a hemiacetal. To draw the product, replace the OH with an OCH3 group. All the other alcohols will be unaffected. They don't react as fast as the hemiacetal. So this one, we're going to replace it with an OCH3 group. Now keep in mind, this is the anomeric carbon, so it can switch between the alpha and beta form. This is the alpha form, where the OCH3 group is facing the upward direction. In the beta form, it can be facing in the downward direction. Now for the test, you don't have to worry about which form it is because it can be in either. And these 2 forms, they're interconverting. So as long as you replace this OH with the OCH3 group, you're okay. That's it. Don't change any other alcohols. So now you know what to do if you see that question on the exam. So now let's go over conjugated systems. Let's say if we have a conjugated ketone. This is the alpha carbon, this is the beta carbon. Now, if you have a very powerful nucleophile, like a Grignard reagent or an organolithium reagent, you need to know that it's going to attack at the carbonyl-carbon. So it's going to attack here. So you get 1,2 addition as opposed to 1,4 addition. In the 1,4 addition, it attacks the beta carbon. So you already know the mechanism between an organolithium reagent with a ketone. We covered that earlier. So it's going to turn into an alcohol, and we're going to add a phenyl, so we get a tertiary alcohol. The double bond will be unaffected. Likewise, if we add a Grignard reagent, let's say methyl magnesium bromide and H3O+, the ketone will be converted into a tertiary alcohol, and the double bond will be unaffected. Now, let's say if you add a weaker nucleophile, or not a weak nucleophile, like a weak base, so to speak, because cyanide's a relatively decent nucleophile. It's going to attack at the beta carbon as opposed to the carbonyl-carbon. So the cyanide ion attacks here, this double bond moves here, and then that's going to open. So here's the CN group. And at this point, this is going to react with water. This oxygen is going to reform the carbonyl group, and this double bond is going to grab a hydrogen, expelling the OH group. So the net result is we get a product that looks like this. If you want to show it, the hydrogen's here, but on most exams, they're not going to show that hydrogen, so it's just going to look like this. So any powerful nucleophiles, they're going to attack at the carbonyl-carbon. The weak nucleophiles, or the weak bases, they attack at the beta carbon. So here's another example. Let's say if we were to use the Gilman reagent, what do you think the major product for this one will be? Now, the Gilman reagent is going to attack the beta carbon because it's the weaker form of the Grignard reagent. So we're just going to add a CH3 to the beta carbon, get rid of the double bond, and that's it. So let's say if we were to add a weak base like ammonia. All we need to do is add the NH2 to the beta carbon, and that will be our answer. So now let's say if we were to add lithium aluminum hydride. This will not react at the beta carbon. This is a very powerful reducing agent, so it's going to reduce the reduce the ketone into an alcohol by the addition of a hydrogen. So we're going to get this. If we were to use a deuterium instead, we would have to show the deuterium. But for the hydrogen, keep in mind, on a test, you won't see it there. Your answer is just going to look like this. Okay, so now let's move on back to like regular ketones. What's going to happen if you add ammonia to a ketone? So let's say if it's not conjugated. What do you think is going to happen? So if you add ammonia to a ketone, you're going to get an imine. What you need to do is remove H2O. So you're going to take away this oxygen and 2 hydrogens, and you get the imine. The imine forms at a pH roughly around 4 to 5. It's very stable at mild acidic conditions. Now, if you add a primary amine, you will also get an imine as well. But you have an R group. Now, if you add a secondary amine, you're going to get an enamine. But now let's say there was a methyl group here. You're going to get this. But there's going to be a double bond, and it's not going to be between the carbon and the nitrogen. The double bond can form either here or it can form here. Now, you want to put the double bond next to the methyl group. That's like the Zaitsev product. This double bond is more substituted on the left side, so therefore it's more stable. So you're going to get this alkane and not this one. So this will be your answer. Alright, so let's say if you have cyclopentanone, and what happens if we add this ylide to it? So you need to know that this is the Wittig reaction. The Wittig or the Wittig reaction converts the ketone into an alkane. So here's what you need to do to quickly draw the product. Replace this oxygen with this group here, the methylene group. And that's how you can quickly get the answer. So let's do some examples. So let's say if we have this particular ylide, all we need to do is replace the oxygen with the group that we see here after the phosphorus. So CH3. That's the answer. Now sometimes you may not see the ylide in that form. Other times it might look different. So they may give you the reagents to make the ylide. Let's say if you have 1-iodopropane with butyllithium and triphenylphosphine. So what I would do is draw out the structure for the 1-iodopropane. So we have a CH3, which is this carbon here, and then a CH2, and then the carbon that has the iodine, which is this carbon, the third one. I would draw it out like this. Carbon, that carbon has 2 hydrogens, and it has an iodine. Now the butyllithium is going to get rid of one of the hydrogen atoms, so this one's gone. And the triphenylphosphine group, it attacks the carbon, it kicks out the iodine, so the iodine's gone too. So what you're going to get is you're going to get the 3 phenyl groups with the phosphorus. The phosphorus is going to attach to this carbon, so then you could just write it double bond and then write it backwards. We have a CH that's left over, and then we're going to write what we see here, CH2, CH3. And then at this point, replace the oxygen with this group. So this is going to be our answer. Let's try another example like that. So let's say if we have 2-butanone and 2-iodobutane with butyllithium, it could be written that way as well, and triphenylphosphine. So now let's redraw the structure of 2-iodobutane. So let's start at this carbon here. That's going to be our center carbon. So I'm going to put it in yellow. We have a carbon. That carbon has a hydrogen. It has an iodine. And on this side we have a methyl. And on this side we have an ethyl. So the butyllithium will remove the hydrogen, but before that happens, the phosphenyl group, the triphenylphosphine group, takes away the iodine. And so what we're going to do is we're going to connect the phosphorus to this carbon by means of a double bond. So we have a carbon double bonded to the phosphorus, and then we have a methyl group on one side, and then an ethyl group on the other side. So that's how we can quickly get our ylide. So now all we need to do is replace the oxygen with this group here. So we're going to get a structure that looks like this. On one side we have a methyl, and on the other side we have an ethyl. So at this point we can redraw it. So let's identify the longest chain. This is carbon 1, 2, 3, 4, 5, 6. So we can draw like this. there's our 6 carbons. Between 3 and 4, we have a double bond. And on 3, we have a methyl, and we also have a methyl on 4. So that's our answer. So let's briefly go over the mechanism. So the triphenylphosphine, what it does is it first attacks the alkyl halide. It's a very good nucleophile, so it favors an SN2 reaction. It's a weak base, but a great nucleophile. So when you draw it, you want to draw it like this at this point. So we have a carbon that has a methyl group. That's this group on the right. On the left, we have an ethyl group. So I'm going to put that here. And we still have a hydrogen, but we're about to remove it. So now when phosphorus has 4 bonds, like nitrogen, it has a positive charge, which means the carbon that is attached to that phosphorus, it has a hydrogen that's relatively acidic. So butyllithium, it acts as a base and gets rid of that hydrogen. So now there's a negative charge on the carbon and a plus charge on phosphorus. So this carbon can use this lone pair to form a double bond. And because of that resonance stabilization of that carbanion, that's another reason why this hydrogen is relatively acidic. So now we have our ylide. Sometimes it can be given to you in this form. Just draw this version and then you can get the answer. So that's the Wittig reaction. That's just the mechanism to form the ylide. There's another part of the mechanism, but we're not going to focus on that. Because once you have the ylide, you can quickly draw the product. Alright, so what's going to be the major product if we add LDA and butyl bromide? And let's say the temperature is like -40. So LDA is a very strong base, and it's going to remove a hydrogen. LDA is lithium diisopropylamide. So there's 2 isopropyl groups on the nitrogen, and the nitrogen has 2 lone pairs, so it has a negative charge, and it's attached to a lithium plus ion. So it's a very strong base, and it's going to get rid of this hydrogen. So we're going to get a carbanion, which is in resonance with an enolate ion. But I'm just going to draw the carbanion at this point. So now, this carbanion will react with butyl bromide. And so this is going to attack the carbon and expel the bromine. So the answer that we are going to get looks like this. So here's another example. So let's say if we use LDA in the first step and then methyl bromide in the second step. All we're going to do is replace an alpha hydrogen with a methyl group. And that's going to be the answer. Now, another thing we have to keep in mind is the formation of a kinetic product versus a thermodynamic product. So let's talk about that at this point. So here, we don't have a symmetrical ketone. So we can remove a blue alpha hydrogen or a red alpha hydrogen. So if we were to use LDA under low temperature conditions like -40, we're going to get the kinetic product. LDA is a relatively bulky base, and so it's going to go for the hydrogen that's most accessible. So under low temperature conditions, typically it's going to form the less stable enolate ion. Which is this one here. Now, let's say if we were to use a base that is not bulky, like sodium hydride, and let's say if we increase the temperature like 60, we're going to get the thermodynamic product, and that's the enolate with the more stable alkene. So at this point, if we were to add methyl bromide, this oxygen can form a double bond, causing this double bond to attack the methyl group. So the methyl group will replace this hydrogen. But if we use LDA, we're going to replace this hydrogen. So let's put this all together. So let's go over let's go over the overall reaction. So if we were to use LDA with a methyl bromide under low temperature conditions, we're going to remove the less substituted hydrogen. That's the secondary hydrogen. And we're going to replace it with a methyl group. So the major product will look like this. Now, if we don't use a bulky base, if we use sodium hydride, and if it's heated, by the way, this is the kinetic product. You get the less stable alkene. It forms faster. But if we use sodium hydride in the presence of heat, followed by methyl bromide, we're going to get the more stable kinetic product, thermodynamic product. And so the methyl group will be here. So that's the thermodynamic product. You need a small base, a small but strong base, and a high temperature. If you use a bulky base and low temperature, you get the kinetic product. So now what happens if we have a ketone and if we add hydroxide with Br2? So in this reaction, we're just going to replace an alpha hydrogen. So hydroxide is going to remove the hydrogen, and we're going to get a carbanion. We could draw the enolate resonance form if we want to, but for this example, we don't need to do that. Now, once we get the carbanion, it's going to attack bromine. And so the net result of this reaction is that we replace an alpha hydrogen with a bromine atom. Now, sometimes you might get a reaction like this. You might get bromine with hydroxide, but excess. If you use excess Br2, you need to replace every alpha hydrogen with a bromine atom. So your answer is going to look like this. You have a bromine atom everywhere. Now, a reaction that's related to this is the haloform reaction. The haloform reaction works well if you have a methyl ketone. So on a ketone, it has to be a methyl group, like a CH3 group. And let's say if we use iodine, excess iodine with hydroxide. The mechanism is very similar to Br2 with hydroxide. The hydroxide is going to take off an H, you're going to get a carbanion, and then it's going to attack the iodine. But because we're using excess I2, it's going to happen 3 times. So after you replace the first hydrogen with an iodine, another base is going to remove the second hydrogen, and then that carbanion is going to attack the iodine. Then another base removes the third hydrogen, and then that carbanion attacks the iodine. And then eventually you get this group, Ci3. You replace all the alpha hydrogens with an iodine group. Then in the next step, the hydroxide can no longer act as a base. There's no more alpha hydrogens for it to remove. So instead it acts as a nucleophile. And then eventually, this is going to reform into a carbonyl, and it's going to expel this group. So the end result is that you get a carboxylic acid. But notice that this solution is alkaline. The pH is very high. So the carboxylic acid doesn't remain in its protonated form. Hydroxide is going to take off this H, and it's going to turn into a carboxylate ion. So you get this. That's the haloform reaction. So let's go over a few things. Let's say if we have this methyl ketone, and if we add I2 with hydroxide, excess, and in another reaction we're going to add I2 with hydroxide in the first step, but in the second step we're going to add H3O+. In the first example, the reaction occurs under basic conditions. So all we're going to do is we're going to replace the methyl group with an oxygen with a negative charge. So we're still going to get a carboxylic acid, but under basic conditions it's going to be deprotonated. In this example, in the second step, we're acidifying the solution. So we're going to get the protonated carboxylic acid. So I just want to make sure I cover the difference between the two. So until you add H2O plus in the second step, it's going to be deprotonated. Otherwise, you'll get this. But on the test, if you don't see this answer, just pick this one. So now let's go over the HVZ reaction. Let's say if we have a carboxylic acid, what's going to happen if we add PBr3? PBr3 will replace the OH group with a Br. So the acid, the carboxylic acid, turns into an acid bromide. Then what's going to happen if we add Br2 with an H plus catalyst? In this example, the alpha hydrogen will be replaced with a bromine atom. But the mechanism occurs under acidic conditions rather than basic conditions. So you're going to get a bromine atom here. Now what's going to happen if you add water to it? Now granted, water can react with the acid bromide and the alkyl halide. But if you have a 1-to-1 ratio, it can't do both. It has to pick one. Now the acid bromide is very, very reactive. And it's way more reactive than the alkyl halide. So water will selectively displace the bromine in the acid bromide, turn it into a carboxylic acid, and the other bromine will remain. So we're going to get this product. Now, by the way, let's say if we were to add ammonia at this point. So after ammonia first will react with the carboxylic acid and remove a hydrogen. So we may need to add like excess ammonia for this to work. So we'll get this initially. But then ammonia will also displace the bromine atom, giving us an amino acid. So this carbon is chiral. So starting from that carbon, on the right we have a carboxylate group. On the left we have an amine group, but it's in its protonated form. Here we have a methyl group, so I'll put that here, and there's a hydrogen which we don't see. So as you can see, this is an amino acid. That's how you can make an amino acid, starting from a carboxylic acid. You need to use the HVZ reaction. So this particular amino acid is known as alanine. So if you want to get different amino acids, you simply need to change the R group here, which is the methyl group. So depending on the carboxylic acid that you choose, you can get different amino acids, but we'll talk about that more later in this video as we go towards reactions that can give us different types of carboxylic acids. But let's move on to our next topic. So now let's go into carboxylic acid derivatives and their reactions. So let's start with an acid chloride. What's going to happen if we add water to it? Now I'm going to draw it this way purposefully. Anytime you add water to any one of the carboxylic acid derivatives, be it an acid chloride, an anhydride, a carboxylic acid, an amide, an ester, not a carboxylic acid, but any one of those other acid derivatives, anytime you add water, you're going to get a carboxylic acid. Anytime you add an amine, you're going to get an amide. When you add an alcohol, you're going to get an ester, and when you add a carboxylic acid, you get an anhydride. Remember those rules. So to quickly get the answer, for this example, remove HCl. and then connect the parts that remain. So you get a carboxylic acid plus HCl, which escapes as a gas. So now let's say if we were to add an acid chloride with an amine group. This time I'm going to color code it. So once again, remove HCl and then connect them. So anytime you add an amine, you get an amide. So now let's say if we were to add an acid chloride with an alcohol. Anytime you add an alcohol, you're going to get an ester. That's if you add it to a carboxylic acid derivative. So remove HCl and simply connect them together. So now, if we have an acid chloride, and if we react it with, let's say, a carboxylic acid, anytime you add a carboxylic acid to an acid derivative, you're going to get an anhydride. So take off HCl and then connect them together. I'm going to draw this part in red. So there's the anhydride. By the way, you need to know the reactivity. The acid chloride is more reactive than the anhydride. And the anhydride is more reactive than the ester. The ester and the carboxylic acid, they're approximately at the same level. And then the amide is weaker. Let me put it on the other side. But it turns out that there's something that's weaker than the amide. That is the deprotonated version of the carboxylic acid. So that's like the weakest. Okay, so now let's say if you have an anhydride. And let's add water to it. Now the best way to see this reaction, or to see the product, replace this group with this group. So anytime you add water, you're going to get a carboxylic acid. So we're going to replace it with an OH. Now let's say if we have an anhydride, and let's say we're going to add an alcohol to it. Anytime you add an alcohol, you're going to get an ester. So replace this group with this group here. By the way, if you want to know what the side product is, the side product is the combination of this group plus the hydrogen. So in both cases, it's going to be a carboxylic acid. That's the side product for all of these reactions. So now let's say if we have an anhydride and we wish to add an amine to it. So replace this group with the amine, but make sure to remove one hydrogen from the amine. So the amine had two hydrogens, but it has one left now. So anytime you add an amine, you get an amide. So now let's start with a carboxylic acid. So if we add another carboxylic acid, what you need to do is, there's two ways you can see this. You can just pretty much get rid of water and then connect the two groups together. So when you add two carboxylic acids together, you get an anhydride. Another way you can see this is you can replace the OH group with this group. So there's two different ways you can view it. But for me, I just like to simply remove water and get the product. So if we have a carboxylic acid, and let's say if we add an alcohol to it, in this case phenol, just remove water and then connect them. By the way, sometimes they may put like radioactive labels on these atoms. And so let's say if this is oxygen 18. You need to know where in the product oxygen 18 is, and it's going to be this oxygen. This oxygen here it leaves, so it's not going to be part of the product. So let's say if oxygen 18 was this one, it's going to be here. This oxygen is right here, and this one remains. This is the one that leaves. Now, what's going to happen if we add a carboxylic acid and an amine? Do we get an amide? Well, it depends on what the reaction conditions are. Naturally, when you add an amine with a carboxylic acid, it doesn't immediately turn into an amide. The first thing that happens is you get an acid-base reaction. And so you're going to get a salt. You get ammonium and a carboxylate group. However, if you add heat, and I'm talking about a lot of heat, then you can get the amide by means of a dehydration reaction. Notice that we lost 2 hydrogens and an oxygen. So once you generate water, when you heat up water a lot, it's going to turn into steam and it pretty much leaves. And as it leaves, you drive the reaction towards the right. But the addition of water would cause the reaction to go to the left. So to drive it towards the right, to get the amide, you got to heat it up so much that water evaporates away. And then the system has no choice but to form the amide. So just make sure you add a lot of heat to get that job done. So now let's talk about some cyclic reactions. So let's say if we have 2 carboxylic acids together. What's going to happen if we add heat to the system? Usually when you add heat, some type of volatile compound escapes. It can be whatever gas that you can form will escape. In the presence of heat, water is going to be the volatile compound. Now water is a liquid at room temperature, but when you heat it above 100, it turns into a gas. It becomes steam. And so a dehydration reaction will occur. And as we said, anytime you add 2 carboxylic acids together, you're going to get an anhydride. But it turns out there's another way to get an anhydride as well from that same compound. And the compound that you want to use is SOCl2. If you add SOCl2, it converts the carboxylic acid into an acid chloride. But it doesn't happen simultaneously. One of the carboxylic acids turn into an acid chloride. Now keep in mind, you don't get both of them, both acid chlorides immediately. As soon as the first acid chloride is generated, it reacts with the carboxylic acid. And I mean, it reacts quickly. And so when these two react, you're going to remove HCl. And when you remove HCl, it turns into an anhydride. So make sure you're aware of this reaction. Because as soon as you get that first acid chloride, it's going to react with the carboxylic acid. And we covered that earlier in this video. An acid chloride plus a carboxylic acid, when you take away HCl, will convert into an anhydride. So sometimes you might see a question like this. Let's say if you have a carboxylic acid, and let's say we have 100% of it. And let's say if we add 1/2 equivalent of an SOCl2. That means if we have 1 mole of a carboxylic acid, we're adding 0.5 moles of thionyl chloride. So that means that thionyl chloride will convert half of the carboxylic acid into an acid chloride. So you're going to have 50% of the carboxylic acid left over and 50% of the acid chloride formed. So if we start with 1 mole of the carboxylic acid and we add 0.5 moles of SOCl2, we now have 0.5 moles of the acid chloride and 0.5 moles of the carboxylic acid. So now we have an equal ratio of the acid chloride and the carboxylic acid. So these two will react and form the anhydride. So the only way to pretty much get this product is you need to add excess SOCl2. but in actual practice, you will get some anhydride from this reaction. So now let's say if we have a cyclic anhydride. What's going to happen if we add water to it? Anytime you add water to any carboxylic acid derivatives, you're going to get a carboxylic acid. Anytime you add water, you get a carboxylic acid. But let's go through the mechanism for this process so you can see it yourself. So water is going to attack the carbon-O-carbon. So initially we get this group. And then another water molecule will get rid of this hydrogen so that it doesn't leave when the oxygen regenerates the carbon-O group. So now we have an OH, and we have this group right now. So now in the next step, what we could do is we're going to protonate this oxygen so we can turn it into a good leaving group. Whenever oxygen has a positive charge, it's a very good leaving group. So this is going to regenerate the carbon-O group, and it's going to break this bond. And so it's going to open into two carboxylic acids. So that's the answer for that reaction. So now, let's say if we have an anhydride. What's going to happen if we add an alcohol instead? So anytime you add an alcohol to a derivative, you're going to get an ester. The leaving group is going to be a carboxylic acid. So this is going to attack here, just like before. And right now, we can't regenerate the carbonyl group because we need to get rid of this hydrogen. Otherwise, it's going to kick out the methanol. Actually, we shouldn't have used water. We should use another methanol molecule to get the job done. So this oxygen is going to grab a hydrogen. So now, we're going to use our protonated methanol group to deliver a hydrogen to this oxygen. So once it's a good leaving group, we can now open the ring. So this is going to reform into a carbonyl group, expelling the other carboxylic acids. So what we're going to get is an ester and a carboxylic acid. So now let's say if we have an anhydride and if we wish to add an amine. So at this point you can probably see what the answer is going to be now. Anytime you add an amine, you're going to get an amide, but the leaving group will still be a carboxylic acid. So this part is going to be the amide. We're going to lose the hydrogen, and then on the other side we're going to have a carboxylic acid. So now, what's going to happen if we have an amide and if we wish to add POCl3? POCl3 is a dehydrating reagent, and so it removes water. And when you remove water, all you're going to have left over is a carbon and a nitrogen if you take away H2O. So here's the carbon, and here's the nitrogen. You're just going to get a nitrile. Now, if you decide to add H3O plus to a nitrile, it will convert to a carboxylic acid. And if you add H3O plus to an amide, but you might need heat to get this working, it will also convert to a carboxylic acid. But amides are not reactive, so you need a lot of heat. So now let's continue the discussion with reactions of amines and synthesis of amines. What's going to happen if you have an amide and if you add lithium aluminum hydride to the amide in the first step, and in the second step, let's say if you add water to it, what's going to happen? Now this is a reducing agent. It's going to reduce the carbonyl group completely. Not into an alcohol, but it's going to put two hydrogens there. So this will go down to an amine. So you don't get this product. It's not going to be an OH. This is different. You get this amine. So now let's say if we have an amide again. What's going to happen if we use bromine with hydroxide and water? Now this reaction is known as the Hofmann rearrangement. What you need to do is get rid of a carbonyl group. And so you're going to lose a carbon and you're going to get an amine. Your byproduct is carbon dioxide and water. Now you need to know the intermediate of this reaction, and it's an isocyanate group. And so it looks something like this. Now you can look up the mechanism, but just know what the end product is for this reaction. Just take away carbon and then it's going to be amine. So let's say if this was the compound that we had. Let's say if we had Cl2 with hydroxide and water, it works the same way. All we're going to do is get rid of the carbonyl group. And so we're going to get an amine. So now what happens if we have an acid chloride and if we choose to add sodium azide with water followed by heat? In the first step, the chlorine will be replaced with the azide group. And once you add water and heat, it's going to rearrange. You're going to get the isocyanate intermediate. But in the end, you're going to lose this entire group. Now, out of those three nitrogens, one of them will remain, and it's going to turn into NH2. The other two nitrogens will leave as nitrogen gas, and it's just going to escape from the solution. It's a very good leaving group, but you still lose a carbon, and you do get a primary amine. So that's the Curtius rearrangement reaction. Now, there are other ways that you can make an amine. Let's say if you have an alkyl halide. If you add NaN3, the N3 group replaces the bromine. And if you draw it out, it looks like this. The nitrogen at the end has two lone pairs, so it has a negative charge. When nitrogen has 4 bonds, it has a positive charge. The other one is neutral. Now from this compound, you can reduce it with LaH followed by water, or you can use like hydrogen gas with a palladium catalyst. Well, actually, I don't think that's going to work. That works for other examples. I'm not sure about that one. But this one will reduce it. It's going to turn it to an amine. So we went from butyl-bromide to butanamine. Or 1-butanamine. So now let's say if we have the same alkyl halide. What's going to happen if we add sodium cyanide to it? For this reaction to work, we may need a phase transfer catalyst because butobromide is not really polar, it's relatively nonpolar. And here we have something ionic, so ionic compounds don't really dissolve in a nonpolar solvent. Now you can use a crown ether to make this work, or you can use a quaternary ammonium salt. It could be chloride, bromide, iodide, all of it could work. But the phase transfer catalyst, which is this quaternary ammonium ion, it transfers the cyanide into the nonpolar organic solvent. And so it allows the cyanide to react with the alkyl bromide at a much faster rate. So you may want to look up phase transfer catalyst when you get a chance. But after this reaction, we're going to replace the cyanide with the bromide. It's going to be an SN2 reaction. Now at this point, there's two ways we can reduce it. We can add lithium aluminum hydride followed by water, or we can add H2 and palladium gas. Either case, both the carbon and the nitrogen will gain 2 hydrogen atoms. So we can write it like this. So we now have 5 carbons instead of 4 with an NH2. So this is how you can get an amine by the extension of 1 carbon atom. So now what's going to happen if we have a ketone and if we add ammonia? Now we talked about this reaction already. We're going to get the imine if we add a nitrogen that has more than 2 hydrogens. So it looks like this. Now if we add H2 with nickel or even lithium aluminum hydride, we can reduce the imine into an amine. So this is known as reductive amination. Now let's say if we choose to add a primary amine, we will also get an imine, but with an R group. Now at this point, you don't want to use NaBH4 or lithium aluminum hydride. You want to use a weaker version of NaBH4, and that's NaBH3CN. This reaction selectively reduces the imine, but it doesn't react with the ketone. So we're going to get, well, if it does react with the ketone, it's very, very slow. But we're going to get this reagent, a secondary amine, rather than a primary amine. But now let's talk about what could happen if you were to use a different reagent. So let's say if you have a ketone, and in the first step we're going to add ammonia, and in the second step let's use NaBH4. Now we can still get the imine, and we can still reduce the imine to a primary amine. So we can still get this answer. However, the imine is in equilibrium with the ketone, and so therefore the NaBH4 can also reduce the ketone, so we can get a side product. We can get both of these products. But now, let's say if we were to use ammonia and the deactivated form of sodium borohydride, in this case sodium cyanoborohydride. This weakened version, it reacts with the more reactive imine as opposed to the ketone. So for the most part, we get a higher yield of the primary amine. And pretty much we don't get this product as much. It's going to be very, very low. So that's why this is the reagent of choice if you want to reduce an imine to an amine. So now let's say if we have a ketone, and let's use a secondary amine this time. So initially, you're going to get the N-amine. And let's say if we have a methyl group here, the double bond is going to be closest to the methyl group. We're going to get the most substituted alkene. And at this point, we can reduce it with NaBH3CN, or H2 with palladium. And the double bond is just going to disappear. So what we're going to get is a second, in this case, a tertiary amine now. So that's how you can make tertiary amines. So now what's going to happen if we have this secondary amine, and if we add excess methyl iodide with silver oxide in water, what's going to happen? Well, this reaction is known as exhaustive methylation, and we're going to add 3 methyl groups to the nitrogen. So we're going to get a quaternary ammonium salt. So the nitrogen has a plus charge. Now the iodide ion, it reacts with silver oxide. It combines with silver and displaces the oxygen. So we get a side product, silver iodide, which falls as a solid. And then the oxygen with a negative charge reacts with water, turning into silver hydroxide, which is also a precipitate, but we get hydroxide. So we get this as well. This reaction is associated with the Hofmann elimination. Whenever nitrogen has whenever it has a plus charge, it's a decent leaving group. And we have hydroxide, which is ionically bonded to the nitrogen atom. Now at first, nothing happens at this point. The nitrogen is a relatively bad leaving group, but it's better than an NH2. An NH2 is an extremely, very, very, very bad leaving group, but the nitrogen is still a poor leaving group, but it's better than a regular NH2 because it has a plus charge. So in order to kick out the nitrogen, we have to add heat because it's very hard to leave. Once we add heat, elimination will occur. We're going to get an E2 reaction. The hydroxide is going to grab the less substituted hydrogen. It's going to form a double bond and expel the nitrogen. So we get the Hofmann product. Now, I want to compare this reaction with some other reactions. Earlier in this video, let's say if we have a secondary alkyl halide, we would get an E2 reaction. Now, if you remember correctly, when we use a bulky base like potassium tert butoxide, because it's so bulky, it goes for the more accessible hydrogen. And so we got the Hofmann product. But now, let's say if we were to use hydroxide, which is a non-bulky base, we would get the Zaitsev product. So all of these are E2 reactions, but with different regiochemistries. Now, in this case, bromine is a good leaving group. And because bromine is a good leaving group, when you add hydroxide, you get an alkene-like transition state. So hydroxide will give you the most stable alkene. That's the Zaitsev product. But if you add a bad leaving group like fluorine, the hydroxide is going to give you the Hofmann product for the most part. Now, as hydroxide grabs the hydrogen, the fluorine doesn't leave immediately. It takes its time because it's a poor leaving group. So you get this buildup of negative charge. And eventually, the fluorine will leave. And you're going to get the Hofmann product. Now, because you get that buildup of negative charge, you get a carbanion-like transition state. And if you think about it, secondary carbocations are more stable than primary carbocations. But the reverse is true for carbanions. Primary carbanions are more stable than secondary carbanions. So, when the hydroxide goes for the primary hydrogen, we get a more stable carbanion transition state. And that's why it doesn't go for the secondary hydrogen, which is the green hydrogen here, because we get a less stable carbanion transition state. Remember, primary carbanions are more stable than secondary carbanions, and that's why we get the Hofmann product. Now, in this case, when we have a nitrogen with 3 methyl groups, the nitrogen is a bad leaving group. So the hydroxide is going to go for the primary hydrogen, so we can get a more stable carbanion transition state. And so we get the Hofmann product. So anytime you have a bad leaving group, you're going to get a Hofmann product. If you have a good leaving group and a non-bulky base, then you get the Zaitsev product. So the strength of the leaving group really also has a factor in terms of which alkene you're going to get. So now let's talk about the Cope elimination. So in the Hofmann elimination, we had a quaternary ammonium atom But in the cope elimination, we're going to have a tertiary amine. So notice that the nitrogen does not have a plus charge. So in the first step, we're going to add hydrogen peroxide. Hydrogen peroxide will oxidize the amine into an amine oxide. So at this point, the nitrogen has a plus charge. Both the cope elimination and the Hofmann elimination, the regiochemistry is you get the Hofmann product, you get the anti-Zaitsev product. So in this reaction, I probably should put the oxygen on the right side. This oxygen is going to grab this hydrogen, and it's going to form a double bond and kick out the nitrogen. So we get the less substituted alkene. So now let me show it here, because you need to understand the stereochemistry of this reaction. The Hofmann elimination reaction is an anti-elimination reaction. However, the cope elimination reaction is a syn elimination reaction. By the way, you need heat to make this work. So once you add heat, this oxygen grabs the hydrogen on the same side. So these two have to be syn with respect to each other. Then we're going to get a double bond, and then the nitrogen will leave. So it's a great way of converting amines into alkenes. So these are like deamination reactions. You're removing the... So let's try this example. Let's say that we have a methyl group in the front and one in the back. So both of these carbon atoms are tertiary. And on this secondary carbon, we're going to have a nitrogen with a plus charge and 3 methyl groups. So this is going to be the Hofmann elimination. And let's say there's hydroxide somewhere in the solution. So once we add heat, will hydroxide remove the red hydrogen, or will it remove the blue hydrogen? Notice that the hydrogens have the opposite steric configuration of the methyl groups that are attached to the same carbon as they are. Now, for the Hofmann reaction, you need to know that it's an anti-elimination reaction, in the sense that the hydroxide is going to go for the hydrogen that has the opposite configuration to the nitrogen. So the nitrogen's on the wedge, the hydroxide is going to go for the hydrogen on the dash. So that's the blue hydrogen. And so we're going to get a double bond over here. So in this case, the stereochemistry determines the regiochemistry. Now this carbon is no longer chiral, so we don't have to put the methyl group on the wedge. So now let's talk about the cope elimination. So this time we won't have a nitrogen with a plus charge. Rather, we're going to have a tertiary amine. But after we oxidize it with hydrogen peroxide, it's going to be an amine oxide, at which point the nitrogen will have a plus charge. So that's after we add H2O2. But in the next step, we're going to add heat. So here we have a hydrogen in the back and one in the front. And let's say the nitrogen group is in the front as well. So this time, for the cope elimination, we're going to get, it's a syn elimination. So the oxygen is going to go for the red hydrogen, because it's syn with respect to the nitrogen. They're both on the same side. And so this time, the double bond will be on this side. So as you can see, we can get two different products here depending on if we decide to use the cope or the Hofmann elimination. Just remember, the cope elimination is a syn elimination reaction, and the Hofmann is an anti-elimination reaction. Now, going back to the formation of imines, we know that if we add NH3 to a ketone, we're going to get an imine. But let's say if you add like a semi-carbazone group. So let's say there is an H2N, a carbonyl group, an NH, and an NH2. So what product do we get with this reaction? Which nitrogen attacks the carbonyl group? Each nitrogen has a lone pair. So is it going to be A, is it going to be B, or is it going to be C? A quick way to tell is looking at the functional groups. A is similar to an amide because it's right next to a carbonyl group. B is also an amide, but C is different. C is an amine. So this is the nitrogen that's going to attack the carbonyl group. It's more reactive. Here's why. If you look at the other nitrogen atoms, those lone pairs are not nucleophilic. This lone pair is busy resonating with the carbonyl group, and the same is true for the other lone pair. It can resonate with the carbonyl group as well. So those lone pairs, they're deactivated as nucleophiles. They're not very nucleophilic. So this is the nitrogen that's going to attack the carbonyl group. So when we draw the imine, we're going to take off 2 hydrogens from this nitrogen, and then we're going to connect everything else. So next we have the NH, then the carbonyl group, and then the other NH2. So make sure you connect this nitrogen to the carbonyl group. So let's try this particular problem. Let's say if we have a ketone and a carboxylic acid attached to the same molecule. What's going to happen if we add a Grignard reagent? Now, the Grignard reagent, it's not going to act as a nucleophile and attack the carbonyl carbon. It's not going to do that. Rather, it's going to act as a base. It's going to abstract a hydrogen. Anytime you have any acidic hydrogens, the Grignard reagent is going to act as a base. And so you're going to get a carboxylate ion, methane gas, and the magnesium and the bromide ion will be ionically bonded to the carboxylate group. So this is going to deactivate the Grignard reagent. So just make sure you're aware of that. Anytime you use a Grignard reagent, if there's any acidic hydrogens, it's going to remove the hydrogen first. What functional group do we have in this molecule? Is this an amide or is it something else? How would you describe it? What's the difference between this functional group and this one? They're not both esters. On the left, we have an ester. On the right, this portion may look like an ester, but it's a completely different compound. This is an anhydride. And we know anhydrides are much more reactive than esters. This is an amide. So if that's an amide, then what is this? This is a phthalimide. It's different from an amide, and it's used in the Gabriel synthesis reaction. So in the first reaction, we're going to use potassium hydroxide. In step 2, we're going to add 1 bromobutane. And in step 3, we're going to use hydrazine. What do you think the product for this reaction will be? The product is going to be a primary amine. All we need to do is replace the bromine with an NH2 group. That's going to be the main product. That's the one that we want. Now the side product, if we use hydrazine in the third step, we're going to get something that looks like this. This is the side product. So as you can see, these 2 nitrogen atoms, they incorporate themselves into this ring. As the ring expands from a 5-atom ring to a 6-atom ring, it becomes more stable. But the end result of the Gabriel synthesis reaction is a primary amine. So now, let's say if we start with the phthalimide again. In the first step, we're going to use sodium hydroxide. And in the second step, we're going to add an alkyl halide. And in the third step, we're going to use H3O plus with heat. So what amine will we get in this product, or in this reaction? All we need to do is replace the bromine with an NH2 group. And so this is our primary product. And the side product, it's going to be a little different. Anytime you add water to a carboxylic acid derivative, you're going to get a carboxylic acid. Here, this phthalimide is similar to an amide. So we're going to get two carboxylic acids in this case. The leaving group is basically this compound. In the mechanism, hydroxide removes the hydrogen, and then you get like a negative charge on the nitrogen. So once you get this nitrogen with a negative charge, it's going to attack this carbon and expels the Br. So that's why we connect the nitrogen on that carbon. And then when you add H3O plus, this bond is going to break and this bond is going to break, and thus it frees the nitrogen. And that's how you get this particular compound. But for the most part, if you see this reaction on a test, all you need to do is replace the bromine atom with an NH2 group. But if you want to know what the intermediate answer looks like, it looks like this. After you remove the hydrogen, and after the nitrogen attacks the carbon when it expels the bromine, you're going to get something that looks like this. And then when this bond breaks, the nitrogen will grab two hydrogens, usually from the solvent, and then you get a primary amine. So now let's go over some reactions associated with benzene rings. So starting from benzene, what's going to happen if we add nitric acid with sulfuric acid? So this is an electrophilic aromatic substitution reaction. And in such reactions, we're going to replace the hydrogen with an electrophile. And in this case, the electrophile is the nitronium ion. That's the intermediate of this reaction. It's NO2. So it looks like this. It's a nitrogen with two oxygens, both with a double bond. And the nitrogen has a plus charge. In this reaction, the benzene ring acts as a nucleophile. The nitric acid is the electrophile. For the most part, all acids are electrophiles, generally speaking. Bases are usually nucleophiles. So now what's going to happen if we add bromine with a Lewis acid catalyst, iron 3 bromide? Now you need to know that the nitro group is a meta-directin deactivator. It deactivates the ring, so it makes it less reactive, but it still can work. So ortho is 1,2, meta is 1,3, para is 1,4. So the nitro group, we're going to say that's carbon 1. And since it's a meta-director, it's going to direct the bromine to the third carbon relative to itself. So it's going to tell the bromine to go there. If it goes on the other side, it's the same. So we're going to get one product in this reaction. So now, after that step, let's say if we add a sulfur trioxide with sulfuric acid, what's going to happen? So the nitro group is a meta-director. The NO2 group wants it to go here. Now bromine is an ortho-para director. Bromine will direct a new group to go ortho to it. That's 1,2, or this position is also ortho. or it can go in a para position. So these two groups, they don't agree with each other. One guy is saying, hey, go over here. Bromine is saying, no, go over there. But who's stronger? Who has more priority? Now, the bromine group, it's a weak deactivator. The nitro group is a strong deactivator. So bromine is more activating than the nitro group. So therefore, bromine is going to tell the SO3 where to go. So it's not going to go in this position, so we can eliminate it. So now we're between this, and this position. Now, on the right side, there's too much steric hindrance on that side. So it's not going to go here because it has to like interact with the nitro and the bromine group. So it's more likely to go in this position or in this position. But I'm just going to draw one of the products. But keep in mind, you can get the other product as well. So I'm going to put the NO2 in its original position and leave the bromine on that carbon. And so the SO3H group, I'm going to write it here. There it is. By the way, if you have a sulfonic acid, if you add heat, you can remove the SO3H group with a hydrogen. You may need an acid catalyst as well. But this is a desulfonation reaction, so excessive heat can drive away sulfur trioxide. So just keep that in mind. So you can go from benzene sulfonic acid back to benzene. So now, let's say if we start from benzene and we're going to add methyl chloride with aluminum chloride. So this is the Friedel-Crafts alkylation reaction. And in this reaction, we're just going to replace a hydrogen with a methyl group. The Lewis acid helps remove the chlorine, causing the methyl group to become electrophilic. So now what's going to happen if we add Cl2 with AlCl3, or even FeCl3? Let's use FeCl3 for this particular example. Now, the methyl group is an ortho-para weakly activating group. So it can tell the chlorine to go ortho or para. So we can actually get a mixture of products. But I'm going to draw the para product for now. So I'm going to use that for my next example. So now, let's say if we add potassium permanganate with H3O+. Just, by the way, keep in mind that you can also get the ortho product. I'm just going to write it here. But now, what's potassium permanganate going to do in this reaction? This oxidizing agent is going to oxidize the methyl group into a carboxylic acid. And that's just something you need to know. It's rare that you'll have to know the mechanism for that, but just make sure you know what the end result is for that reaction. So starting with benzene again, what's going to happen if we add ethyl chloride with aluminum chloride? So once again, we're going to replace a hydrogen with an ethyl group. And then what happens if we add I2 with nitric acid? The nitric acid is going to oxidize the iodine, and so you get like an I plus cation, which is electrophilic. Now, the ethyl group, just like the methyl group, is an ortho-para director. So this time I'm going to draw the ortho product. But you can also get the para product. So let's put the iodine here. Here's the other product. So starting with the ortho product, what's going to happen if we add sodium dichromate with sulfuric acid? Now, like potassium permanganate, sodium dichromate with sulfuric acid is also a very strong oxidizing agent. Even though there's two carbons here, it's going to oxidize this group into a carboxylic acid. If there was 3, 4, 5 carbons, all of them will be oxidized into CO2. Only the benzyl carbon will remain, so you're going to get like a benzoic acid functional group, regardless of how many carbons are attached to that chain. So this is going to be our answer. So now, what's going to happen if we add tert butyl chloride with AlCl3? This too is a Friedel-Crafts alkylation reaction, and it's just going to add a tert butyl group. Now, what if we added propyl chloride with aluminum chloride? Now, the tert butyl group is an ortho pair director, so it can direct it to the ortho position and the para position. But we're not going to get the ortho product in good yield because this is a very bulky group and it's going to be hard for the electrophile to approach it at that side. So we're going to get the para product with a very high yield. So on a test, you should only put the para product in this case if you have a very bulky group. But now you need to know that the Friedel-Crafts alkylation reaction can rearrange. For tert butyl, it didn't rearrange because the chlorine was already on the most substituted carbon, and that was the tertiary carbon. For ethyl chloride, it wouldn't rearrange because the chlorine was on the primary carbon and there was nothing higher. But for propyl chloride, it can rearrange because the chlorine's on the primary carbon, but there's a secondary carbon. The Lewis acid catalyst will remove the chlorine group. You're going to get a primary carbocation, which will rearrange into a secondary carbocation. Now, sometimes a hydride shift may occur, which will prevent the formation of a primary carbocation, so you can get the secondary carbocation immediately. But either case, regardless of whichever mechanism actually occurs, you need to connect the benzene ring to the secondary carbon, not the primary one, and that's what you want to remember for this step. So you're going to get this. So sometimes you might see this on the test. Instead of propyl chloride, you might see butyl chloride. And the same principle will apply here. So the chlorine is attached to the primary carbon, but make sure you attach the secondary carbon to the benzene ring. So now, the tert butyl group wants to direct it in the ortho position, but the isopropyl group is also an ortho pair director, and it wants to direct it to the ortho position relative to itself. So these two groups are competing against each other, and they're both weakly activating groups. However, we don't want to put anything next to the tert butyl group, so we're going to put the new group on this position. So here's what we're going to do. We're going to connect the benzene ring to this carbon. The Cl is going to leave. So here's our first carbon atom. On the right side, we're going to have a methyl group, so I'm going to indicate that in blue. On the left side, we have an ethyl group relative to the secondary carbon, so I'm going to indicate that in red. So you get like a sec-butyl group. So now, what's going to happen if we choose to oxidize it with potassium permanganate? You might see other oxidizing agents, like sodium dichromate. You can see chromium trioxide with HCl can work. But typically, it's either going to be this or sodium dichromate with sulfuric acid as the oxidizing agent. So will all the alkyl groups be oxidized, or will just some of them? What you need to know is that the tert butyl group will not be oxidized. It's going to remain unaffected. All the other groups will be oxidized into a carboxylic acid. And regardless of the number of carbons that you see, all you need to put is a COOH. That's it. Only one carbon will remain. Now let's talk about why. This carbon atom is a quaternary carbon, and so there's no benzylic hydrogens on it. So that's why it's unaffected or resistant towards oxidation. This carbon is tertiary, so it has a benzylic hydrogen. Therefore, it's susceptible to oxidation. And this one is also tertiary. It has a benzylic hydrogen. So the only way it won't be oxidized is if there's no benzylic hydrogens. It has to be a quaternary carbon. So this is going to be the answer for that reaction. So if the Friedel-Crafts alkylation reaction, if it causes so many rearrangements, how can we get this product? Because if we were to use propyl chloride with aluminum chloride, it's going to rearrange. The benzene ring is going to attach at the secondary carbon. So how do we make this? You need to use the other version. You need to use the Friedel-Crafts acylation reaction. So let's say if we use an acid chloride with the aluminum chloride catalyst, all you need to do is get rid of the Cl and connect the benzene ring to what's left over. So this part is going to attach to the benzene ring. So we get that. Now in the next step, we can reduce the ketone using two common methods. The first one is zinc mercury with HCl. This is known as the Clemmensen reduction. Or you could use the Wolff-Kishner reduction, which is hydrazine in the presence of a strong base, potassium hydroxide. So one is acidic, the other is basic. And what's going to happen is all you need to do is get rid of the carbonyl group. And so you're going to replace it with two hydrogen atoms, but we don't have to show the hydrogen atoms. So we get propylbenzene. That's how you can make it. It's a two-step process. So now, once we have this compound, what's going to happen if we add NBS? Now, for this reaction, sometimes you might see heat with NBS, and sometimes you might see a peroxide, like hydrogen peroxide. It doesn't matter. If you see NBS with heat or with peroxide, it's going to have the same exact effect. All you need to do is replace the benzylic hydrogen with a bromine. So put a bromine one carbon away from the benzene ring. So we're going to add a bromine on a benzylic carbon. If it's on any other carbon, it is wrong. So now, once we have this compound, what's going to happen if we use tert-butoxide or potassium tert-butoxide with tert-butanol? So this is a strong base. And it's going to remove a hydrogen that's adjacent to the carbon-bromine bond. So it's going to go for this hydrogen. This is an E2 reaction, and it's going to form an alkene. So now we have a benzene ring with an alkene on the outside. Now this alkene is relatively stable because it's conjugated with the benzene ring, but we can still do some reactions here. So what's going to happen if we add borane with tetrahydrofuran, followed by hydrogen peroxide and hydroxide? So this reaction will put an OH on the alkene. Now, because they're both secondary, it doesn't matter where the alcohol can go, so it can go in both places. So let's put it here. We can also use mercury acetate with water and sulfuric acid, so that can work too. Now, if we want to, we can oxidize the alcohol into a ketone with PCC. And from here, we can do all sorts of things. So let's see. Let's add ammonia. If we add ammonia to the ketone, what's going to happen? Anytime you add an amine or a nitrogen that has at least two hydrogens on it, you're going to get the imine product. Now, if we want to, we can reduce that to an amine. And so now we have an NH2 outside of the ring. But now, starting with this, what we also can do is add a Grignard reagent to it. So let's say if we wanted to add butyl magnesium bromide in the first step, and then in the second step, H3O+. We know the mechanism. This is going to attack the carbon, and then this bond is going to break. It's going to turn into an alkoxide ion, an O-, and then it's going to grab a hydrogen from H3O+. So it's going to be reduced to an alcohol. But anytime you add a Grignard to a ketone, you're going to get a tertiary alcohol. So here's the OH, and we need to add the butyl group. So 1, 2, 3, 4 carbons. Now we can also do something else. Let's say if we want to convert the alkene into an alkyne, because sometimes you'll have a lot of side chain reactions, and you have to know what's going to happen. And if you're going to have synthesis problems on your tests, sometimes you need to make an alkyne. If you want to go from an alkene to an alkyne, here's a simple way you can do it. First, add bromine with like dichloromethane or carbon tetrachloride, CCl4. So we're going to add 2 bromines across the double bond, but we're not going to be concerned with stereochemistry at this point. But keep in mind that this reaction proceeds with anti-addition. Now, once you have 2 bromine atoms, the best way to convert it into an alkyne is to use sodium amide, NaNH2. So let's go over the mechanism for this process. This is an E2 reaction. So the NH2 minus ion is going to grab a hydrogen. It's going to form a double bond and expel one of the bromine atoms. So we've regenerated our alkene, and now there's another bromine that we can remove. And so we need 2 equivalents, by the way, of this sodium amide reagent. So the second one is going to react by means of another E2 reaction. So this is going to grab the hydrogen. We're going to form a double bond and then expel the bromine atom. So now we have an alkyne. By the way, if you have a benzene ring, what's going to happen if you add carbon monoxide, hydrochloric acid, aluminum chloride, and copper chloride, or copper 1 chloride? This reaction is known as the Gadman-Koch formulation, and what it does is it creates a benzaldehyde. It's a nice way to make benzaldehyde. The intermediate of this reaction is an unstable acid chloride group. Well, it has like an acid chloride functional group, but it also has like an aldehyde functional group as well. So the combination of those two is probably something different than an aldehyde or acid chloride, but it's unstable. But let's move on. Now, let's say if you have a benzene ring with 2 different alkyl groups. Let's say you have an isopropyl group and a propyl group. What's going to happen if you add NBS to it? Now, you can get 2 different products. We can replace the hydrogen here because that's a benzylic hydrogen, or we can replace it with a Br on the other one. So we're going to draw both because we can get both products. However, it turns out one is better than the other. So while I draw these 2 products, see if you can decipher which one is the major product. Is it compound A or is it compound B? The correct major product is compound A. The reason being is this carbon is tertiary, and in compound B it's secondary. Now, this reaction proceeds by means of a radical. Tertiary radicals are more stable than secondary radicals. In fact, that's a tertiary benzylic radical, so it's stabilized by resonance as well. This one is stabilized by resonance, but it's secondary, so choose the one that's tertiary if you see that on the exam. So now sometimes you might get a situation where you see like two benzene rings, and you have to decide on which ring will you add whatever you're trying to add. Let's use bromine with iron 3 bromide. So, should we add the bromine to the ring on the left or to the ring on the right? That is the question. So you need to find out which ring is activated. So, in an EAS reaction, in an electrophilic aromatic substitution reaction where you replace the hydrogen with an electrophile, you need to know that the benzene ring is nucleophilic. So the ring that's more activated is the one that's more nucleophilic. So nucleophiles are associated with negative charges. So which ring is more negatively charged? Let's answer this by means of resonance structure. The carbonyl group is a meta-directin deactivator. It deactivates the ring. And the reason why it deactivates the ring is because it puts a positive charge on the ring. It makes the ring electrophilic. So we're not going to add the bromine to the first ring. That ring is electrophilic. This ring is nucleophilic. This is the right one, but let's see why. So if we draw the resonance structure, this double bond can move here, and then that can open. So what we get is something that looks like this. So as you can see, the carbonyl group puts a plus charge on the benzene ring, so it makes it electrophilic. And so bromine, which is an electrophile, doesn't want to react with another electrophile. It wants to react with a nucleophile. So that ring is deactivated. It's not going to work. It only works if you add like a lot of heat. So now let's look at the other ring. So this oxygen can donate electron density by means of the resonance effect. So it's a very strong activator. As you can see, it can put a negative charge on the benzene ring. And it does so by acquiring a positive charge. So now that the benzene ring has a negative charge, it's more nucleophilic, which it makes it more reactive in EAS reactions towards electrophilic aromatic substitution reactions. The reverse is true for nucleophilic aromatic substitution reactions. So now that we've established that the ring on the left is more reactive, we need to know where on that ring will the Br go. Now we know this is an ortho-para activator, so it can tell the bromine to go on the ortho position or on a para position. Now this group is for the most part pretty bulky, so the para position will be favored over the ortho position. So on the test, if you have to make a decision, 99% of the time it's going to be the para product. If it's the ortho product, I'm sure there must be a good explanation, but I know what I would do. I would go with the para product. So this would be my answer for this particular problem. So now we're not done with benzene rings. There's still a lot to talk about. So going back to this particular benzene ring, let's say if we add nitric acid with sulfuric acid. What do you think is going to happen? We know we're going to get an NO2 group. But now what happens if you add, let's say, a metal with hydrochloric acid? It has to be an active metal. Do you know what's going to happen now? If you add a metal with hydrochloric acid, the metal reacts with HCl, and it creates FeCl2 and hydrogen gas. So basically, we're adding hydrogen. And all you need to do is replace the oxygen with hydrogen. You're going to get aniline, NH2. So in Gen Chem, you've learned that when you add a metal with an acid, it usually creates hydrogen gas. But if you look up the activity series, some metals will react with hydrochloric acid, and some won't. So Sometimes you'll see like zinc with HCl is going to do the same thing, and tin with HCl. All of these metals are above hydrogen on the activity series. You can go to Google Images, look up the activity series. If you were to use like copper with HCl, copper doesn't react with HCl. Silver, gold, they're stable metals. They're not going to react with hydrochloric acid, so they wouldn't work here. Also, if you see SnCl2, this could work too. The tin plus 2 ion is also a reducing agent. It can shoot off 2 electrons, and it can react and generate hydrogen gas. But this could work as well, and it can make aniline. So once we have aniline, I know we kind of got off topic a little. What's going to happen if we add sodium nitrite with hydrochloric acid? By the way, if you see a temperature like 5 or 10, this means this reaction has to be handled in cold solution, because if you heat it up, it can decompose. Now, sometimes instead of seeing sodium nitrite with hydrochloric acid, you might see HNO2. If you do like a double replacement reaction, this creates HNO2 and NaCl. So if you see HNO2, it's the same thing. Sometimes you might see it as HONO. Any one of these will convert the aniline molecule into an arene diazonium salt. Whenever nitrogen has 4 bonds, it has a plus charge. And so chloride is going to be paired to it. And so we get this. So now, starting from that reagent, we can do a lot of stuff. So let's say if we choose to add copper chloride, we're going to replace the N2 group with a chlorine atom. I believe that's known as the Sandmeyer reaction. And if we add, for example, copper bromide, we're going to replace the chlorine group with bromine. I could put the bromine anywhere on the ring because it's the only group on the ring. Now, if we add, let's say, copper cyanide, we're going to get a nitro group. And if we want to, we can reduce that with H2 and palladium or platinum. Sometimes you might see palladium over carbon. It does the same thing. It's going to reduce it into an amine. So it's going to be a CH2NH2, which we can write it this way. If we add H3O+, starting from this, we can get phenol. And if we add fluoroboric acid, HbF4, we can get fluorobenzene. And there's one more reaction you have to know. Let's see if I can fit it in here. If you add H3PO2, this will go back to benzene. It's going to add a hydrogen. So sometimes you might get a question like this. How do you remove an NO2 group from a benzene ring? How do you go from nitrobenzene back to benzene? So first you need to reduce the nitro group to an NH2 group by using a metal and HCl. Then step 2, you want to use nitrous acid, which will convert it into the arene diazonium salt, N2. And then once you use H3PO2, you're going to replace the N2 group with a hydrogen. And so you can go from nitrobenzene to benzene. So all of the reactions that we've considered thus far are are electrophilic aromatic substitution reactions. And in those reactions, you're replacing a hydrogen with an electrophile for the most part. Now, what we're going to consider are nucleophilic aromatic substitution reactions. Instead of replacing a nitrogen, we're going to replace a halogen like a chlorine or a bromine. So, in electrophilic aromatic substitution reactions, orthopara activators, they make the ring more reactive, more nucleophilic. So like OH, OCH3, NH2, they would make the ring more reactive. Now, in a nucleophilic aromatic substitution reaction, the reverse is true. The electron withdrawing groups, like the nitro group, the carboxylic acid, a CF3 or NR3 group, all of those meta-directed deactivators, they're now activators in nucleophilic aromatic substitution reactions. So this nitro group will make the ring more reactive. So keep this in mind. In an electrophilic aromatic substitution reaction, the benzene ring acts as a nucleophile. So electron donating groups, they're going to put a negative charge on the benzene ring, making it more nucleophilic. And that's why OH groups and OCH3 groups, they make the ring more activated. Well, in a nucleophilic aromatic substitution reaction, you're going to replace the halogen with a nucleophile. So if hydroxide is the nucleophile, that means that the benzene ring is the electrophile. So this ring becomes more reactive if it's more electrophilic. And the only way to make it more electrophilic is to add an electron withdrawing group, like a nitro group. So the end result for this reaction is that you're going to replace the nucleophile. You're going to replace the chlorine with the nucleophile. So you're going to get a phenol. So let's talk about the mechanism. By the way, before we do that, let's go over the mechanism for an electrophilic aromatic substitution reaction. And let's compare that with a nucleophilic aromatic substitution reaction. So let's go over nitration. Nitric acid reacts with sulfuric acid, and it creates this nitronium ion, plus some other stuff. So this is going to be an EAS reaction. So in an EAS reaction, we're going to replace the hydrogen with an electrophile, and the benzene ring, remember, is the nucleophile. So the arrow always starts from the nucleophile to the electrophile. Electrons flow from a region of high electron density to a region of low electron density. It's the same way as water flows from a high position to a low position. So in the first step is an addition step. We're adding the NO2 group. If we add the NO2 group on the top, we're going to put a plus charge on the bottom. And then in the second step, some base, it can be maybe water, it could be the bisulfate ion, but some generic base is going to grab a hydrogen, and we're going to form a double bond. So that's the generic mechanism for an electrophilic aromatic substitution reaction. So as you can see, the net result is that we replaced a hydrogen atom with the electrophile, the nitro group. And also sometimes on a test, they may ask you, hey, what is the intermediate of this reaction? For electrophilic aromatic substitution reaction, you need to know that you get carbocation intermediates. There's going to be a plus charge in the ring. Well, for a nucleophilic aromatic substitution reaction, you're going to get a negative charge instead. So we're going to see how we get a negative charge, and also we're going to see why the nitro group makes this ring more reactive towards nucleophilic aromatic substitution reactions. So now this is going to be an NAS reaction. And we're going to use the NH2 minus ion as the base instead of hydroxide. And we're going to put the chlorine here. So in this reaction, the nucleophile attacks first. The electrons, the arrow always go from the nucleophile to the electrophile. So if the NH2 group is the nucleophile, that means the benzene ring is the electrophile. So as it attacks the carbon, this double bond moves here. Well, actually, let's draw the carbanion intermediate first. We're going to put the electrons on this carbon. So we have the chlorine, the NH2 group, and we still have the nitro group over here. By the way, the nitrogen has a positive formal charge since it has 4 bonds. So right now, as you can see, we have a carb-anion intermediate. So for any time you replace the chlorine with a nucleophile, your intermediate is going to have a negative charge and not a positive charge. Knowing that, if you have a multiple choice exam, you can distinguish one answer from another. You can eliminate the wrong choices. So now let's move this negative charge onto this nitrogen atom. So the nitro group is a very powerful electron withdrawing group, and it stabilizes the carbanion because it pulls the electrons toward itself. So this negative charge is going to move towards the nitro group. And notice that the oxygen atom bears the negative charge. Nitrogen it still has a positive charge. So the negative charge is on this oxygen. So that oxygen now has 3 lone pairs. So then how do we remove the Cl? So now this oxygen is going to reform a double bond. And this double bond moves back, and then that moves back here, and then the Cl gets kicked out. So that's the generic mechanism for a nucleophilic aromatic substitution reactions. So basically, you're replacing a halogen with a nucleophile. In an EAS reaction, you replace the hydrogen with an electrophile. So by the way, those intermediates that we drew in that example, it's also known as the Meisenheimer complex. There's 2 intermediates you have to be familiar with, the Meisenheimer and the benzene intermediate. Both of these are associated with nucleophilic aromatic substitution reactions. So here's how you tell the difference. If you have an electron withdrawn group, like a nitro group, if you see 1 or 2 of them on a benzene ring, you're going to get the Meisenheimer complex. That's when you get a negative charge on the benzene ring. Now, if you don't see those nitro groups, and if you add a very, very powerful nucleophile / base, like NaNH2, usually this is dissolved in ammonia, you're going to get the benzene intermediate. So the mechanism is a little bit different. Because the NH2 minus ion is a very strong base, it's going to grab the hydrogen. And then we're going to get a triple bond, and then the Br is going to leave. So it's like an E2 reaction, it's like sort of. And so this is the benzene intermediate. We have a triple bond in the benzene ring. But now let's say if we had a methyl group here. We can get a lot of different products. Because keep in mind, we can also get the triple bond on this side as well. Because this double bond here, it can move in the ring. It can be over on this side. So the benzene ring could be written like this too. So what you want to know is that in the end, you can replace the bromine with an NH2, but the NH2 group can go on any one of these 3 carbon atoms. But let's continue with the mechanism. So then the NH2 minus ion attacks one side of the triple bond. It could be on this side or on the other side. And then it puts a negative charge on the other side. So now we have a double bond again, but we have a negative charge. And so here's the NH2 group. So when it reacts with ammonia, NH3, it's going to grab a hydrogen, regenerating the NH2 minus ion. So the net result is that we replace the bromine atom with the NH2. So here's the methyl group. Now, because sometimes you can get a mixture of products. So let's write the overall reaction. So keep in mind, the NH2 group can go on the carbon with the bromine, or it can go 1 carbon to the left or 1 carbon to the right. It can go on any one of those positions. So in this particular example, we get a mixture of 3 products. So we can put the NH2 on this carbon, we can put it on this carbon here. Or we can put it on this carbon here as well. So here's an example. How many different products do you get if you have para-bromotoluene? And let's add sodium amide. So we can put the bromine atom on any one of these carbons. It could be where the Br is, or one carbon away to the right or to the left. So this is one answer. This is another answer. And what about this one? Notice that these two are identical. They're the same. So therefore, you only get two products due to the structure. So even though the NH2 group can go in 3 positions, you need to know if you have identical products or if they're different. In the last example, they were all different. One was ortho with respect to the CH3, the other was meta, the other was para. But this one is a para product, and this one is meta, and so is this one. So since these two are both meta, and as you can see, they're identical. So sometimes you can get 2 products, other times you can get 3. Just, you may have to draw each one and find out which is which. So now let's talk about heterocycles. So this is perol. It's an aromatic compound. It has 6 pi electrons, 2, 4, 6. It's cyclic, conjugated, and all sp2 hybridized. What's going to happen if we react it with methyl bromide? Will the methyl group go on the C2 carbon, or will it go on the C3 carbon? For 5-membered heterocycles, it's going to attack at the C2 position. Make sure you know that. So here's the mechanism. The reason why it attacks at the C2 position is because you get more resin structures. The intermediate is more stable. So this nitrogen is going to move and form a double bond here. This double bond moves here, and then it attacks the methyl group. This reaction works well in an EAS reaction. The ring is nucleophilic, and you're adding an electrophile. You're going to replace it with a hydrogen. By the way, electrophilic aromatic substitution, you want to know that it's an addition-elimination reaction. In the first step, there's a hydrogen here, by the way. We're adding the methyl group. And in the second step, we're going to remove the hydrogen. So we're adding first, then we're eliminating. The Meisenheimer complex, that reaction, is also an addition-elimination. The one that's elimination-addition is the benzyne. Because in the benzyne intermediate reaction, we eliminated the hydrogen and the bromine first, and then we added NH2. So I just want to add that little detail to this, because I forgot to add that earlier. So after we add the methyl group, now we need some sort of generic base. This base is going to eliminate the hydrogen, and we're going to regenerate the aromatic ring. So the nitrogen is going to pull those electrons back toward itself. So as you can see, 5-membered rings, they really work well with EAS reactions. That nitrogen, it can donate electron density to the ring, and so it activates it towards EAS reactions. So the net result is that you replace the hydrogen on a C2 carbon with an electrophile. Now there are some other 5-membered heterocycles that work the same way. The next one is furan. This one is also aromatic. It has 6 pi electrons. 2, 4, 6. Now, if you're wondering which lone pairs should you count and which ones you shouldn't, here's how you tell. If the lone pair makes the 4th group, count it as a pi electron. So for the nitrogen, it looked like this. Count the lone pair last. 1, 2, 3, 4. Those lone pairs are counted. For the oxygen, it looks like this. This is 1, 2, 3. Don't count the third one, but count the fourth one. So we count one lone pair, not both. With a carbanion, it looks like this. 1, 2, 3. This makes the fourth group. Count it as a pi electron. But don't count this one. Now, sometimes you might have like a pyridine ring. This is 1, 2, 3. It doesn't make the fourth group, so do not count it as a pi electron. So that's just something to keep in mind. So now let's try a reaction with this compound. So this will also react at the C2 position. So let's use chlorine for an example. Because this ring is activated towards electrophilic aromatic substitution reactions, we don't need a Lewis acid catalyst like FeCl3. This could react with Cl2 on its own. Now keep in mind, there's a hydrogen here. So the mechanism, as you can see, is very similar to the last one. And then we're going to use a base, which is going to remove this hydrogen. This is going to form a double bond, causing this to move here and that to go there. And so we get this with a Cl. So what do you think the major product will be if we add thiophene with an acid chloride? Once again, we don't need the Lewis acid catalyst. The end result is that we're going to get rid of the chlorine and we're going to add this group. We're going to replace it with the hydrogen. So we're going to get a ketone. So once we have, if you want to see the mechanism, it works like this. This double bond attacks the carbon-O-carbon, causing this to open. And then it kicks out the chlorine group. And then also, you know, the base is going to grab the hydrogen. This is going to form a double bond. That's going to move here. And the sulfur regains its lone pairs. So I just combine both steps into one. So now we have a double bond O. The hydrogen is gone, so those two left as HCl. And we get this. Now let's say if you have pyridine. Pyridine, this ring is actually deactivated towards electrophilic reactions. So let's say if you wanted to do like aromatic nitration, you would have to heat this reaction to like 300 degrees Celsius. It can work, but for EAS reactions, you need to know that you're going to replace the hydrogen on the C3 carbon. This is the C2 carbon. This is also C2 because due to resonance, but we're going to focus on the right side. So this is C3, this is C4. So in this reaction, we're just going to add an NO2 group on the C3 carbon. So let's say if we want to do aromatic sulfonation. Because the ring is deactivated towards, I really messed that up. That's a terrible S. Since the ring is deactivated, we need a lot of heat to make this work. And then on the C3 carbon, we're going to add SO3H. But now pyridine, because it's deactivated towards EAS reactions, it works very well towards NAS reactions. But for that to work, we need like some sort of some leaving group, like a chlorine or a bromine. Now, in an NAS reaction, substitution can occur at the C2 position or at the C4 position. Both can work. So let's use hydroxide in this case. Actually, let's choose a different nucleophile. Let's use methoxide. So anytime you replace a halogen with a nucleophile, you know it's a nucleophilic aromatic substitution reaction. So methoxide attacks the carbon, and then it's going to put a negative charge on the nitrogen. It's always better to have a negative charge on a nitrogen or on an oxygen rather than a carbon. It's more stable that way. So now we have two groups. We have the chlorine, which is a good leaving group, and the OCH3 group, which is a bad leaving group. So then the nitrogen is going to reform the double bond, and it's going to kick out the leaving group that's easier to be removed, and that is the chlorine. So the stronger nucleophile replaces the weaker nucleophile, and so we get this group. So now here's another example. So let's say if there was a bromine atom on that carbon, and let's add NH2 minus. So this is going to attack here, that's going to move there, and then we're going to have two lone pairs on the end. So the nitrogen now bears a negative charge. And so this lone pair is going to form a double bond, causing this to move here, expelling the bromine atom. So as you can see, in any nucleophilic aromatic substitution reaction, it always puts a negative charge on the ring. In this case, the negative charge is on the nitrogen atom, and the halogen gets replaced. So that covers reactions associated with aromatic rings. So now let's move on to alpha hydrogen substitution reactions like aldol reactions and so forth. So if you see an aldehyde with hydroxide, what should you be thinking? In your mind, what is going on? I know I kind of gave you a hint earlier, it's an aldol reaction, but sometimes you might see this on the test and you may not know what's going to happen. If you see this, what I would do is redraw it first as a line structure. You need to know that the base is going to grab the alpha hydrogen. And we can draw the carbanion or the enolate ion. So I'm going to alternate between the two so you can be familiar with both mechanisms. At this point, at this level of organic chemistry, you need to know your mechanisms very well. And so for each of these reactions, I'm going to show the mechanisms because that's the best way to figure out what the product's going to be. Now, the only time I won't show the mechanism if it's not needed. But for most of them, I will. Once we get this carbanion, it's going to react with another aldehyde. So basically, it reacts with itself. And this is going to attack here, and then we can connect the two structures together. And so we get this. And then it reacts with water. So this is going to grab a hydrogen and expel hydroxide. So what we have is known as an aldol. We have an aldehyde and an alcohol together. Notice that the alcohol group is on a beta carbon. If you see the alcohol group not on a beta carbon, you know it didn't come from an aldol reaction. But it doesn't end here because there's something else we can do. Now, if we add heat to this aldol product, dehydration can occur, and that's by means of the E1CB reaction. The E1CB reaction is an elimination reaction, it works for removing poor leaving groups. The hydroxy group is a very bad leaving group, so the E1CB reaction is the mechanism of choice. So once we have this enolate ion, the oxygen is going to use one of its lone pairs to form a double bond, causing this double bond to move here, expelling the hydroxy group. So the end product of the aldol reaction after heat is you get an alpha beta unsaturated carbonyl group. It can be an aldehyde or a ketone. So that was a base catalyzed aldol reaction. So what about an acid catalyzed aldol reaction? So let's do a reaction between a ketone and an aldehyde. This is a cross-aldol reaction, and in such a situation, you can get 4 different products. So let's say this is A and this is B. let me quickly show you how to get the 4 different products. So A can react with B, A can react with itself, B can react with itself, which we did already, and B can react with A. So you can get a mixture of 4 products. So if A reacts with B, the alpha carbon is going to attack the carbonyl carbon. So when you count it, it's going to be like 1, 2, 3, 4, 5. So initially you get the aldol product, which is a carbonyl with an OH group. And then after dehydration, you're going to get a double bond. That's A with B. Now if A reacts with itself, carbon 3 is going to connect to carbon 4. So notice that I start counting here at the carbonyl carbon. So we're going to get 5 carbons in a straight chain. On carbon 4 it's going to be an OH. But notice that carbon 4 also has a methyl group, which wasn't part of the parent chain. And then after we get rid of a hydrogen and the OH group, so that leaves us water, we're going to form a double bond in the middle. So we get that product. And if we react B with B, which we did already, it's going to be 1, 2, after the alpha hydrogen connected to the carbonyl carbon. So we get 4 carbons, an OH on carbon 3, and then once we remove the alpha hydrogen and the OH, we get the alpha beta unsaturated aldehyde. Now B with A, so let's put B first, and then let's add A to it. So we're going to count it this way. This is going to be carbon 1, 2, connect 3 to the carbonyl carbon, and then 4. So don't make this methyl group 3, otherwise you won't get the right answer. So we have a 4 carbon chain. On carbon 3, as always, we have an OH. But carbon 3 has a methyl group, so we're going to put it right there. And then we're going to remove the H and OH. I'm going to flip the methyl group to the top. And so this is the product that we get. So that's how you can quickly draw the products of the aldol reaction. But now let's do an acid catalyzed mechanism, because you need to know what the nucleophile is for an acid catalyzed mechanism. For a base catalyzed mechanism, the nucleophile can be a carbanion, or it can be the resonance form of the carbanion, which is the enolate ion. Both of these are the nucleophiles in a base catalyzed reaction. In an acid catalyzed reaction, the first step, let's use H3O+. The first step is protonation. In a base catalyzed reaction, the first step is deprotonation. So here we have an activated enol. Right now, this is the electrophile. I'm going to put E for electrophile for the aldol reaction under acidic conditions. Under basic conditions, we said this is the nucleophile. The electrophile under basic conditions is simply the carbonyl group. So that's the electrophile under basic conditions. But under acidic conditions, it's the protonated ketone, or carbonyl. Now, if you want to draw the nucleophile for the acidic condition, use water as a base, and water is going to grab the alpha hydrogen, and it's going to turn into an enol. So the enol is the nucleophile under acidic conditions, and it's going to react with the electrophile, which is the protonated ketone. So under acidic conditions, the mechanism is a little bit longer, so I'm just going to do this once. So the OH of the enol, it forms a double bond, causing the double bond that's already there to become nucleophilic and attack the electrophilic protonated carbonyl group. So this is going to be carbon 1, 2, 3, and then 4, 5. So we're going to react the ketone with itself. So on carbon 2, we have the protonated ketone, and on carbon 4, we have an OH. So our next step, what we need to do is we need to use water to grab a hydrogen and form a double bond. We're going to get the enol again. And here we have an OH. Now, under acidic conditions, we can't just kick the OH because that's going to create hydroxide. So since we can't kick out hydroxide, we need to convert the OH group into a good leaving group. And we can accomplish that by protonation. So this oxygen is going to grab a hydrogen. And we're going to get an OH2 group. So now it's a good leaving group. So now this oxygen can form a double bond, causing this double bond to move here, expel in water. Now we're not quite finished yet. So now we need to use water to get rid of this hydrogen. And now we have our final product. And I'm forgetting the methyl groups. There should be a methyl group here. Yeah, sometimes it's easy to forget a methyl group. Mistakes happen, but it should have been there. So this is our final answer. So what if let's say if you have these two aldehydes on the test. Let's say if you see propanol with an Al and benzaldehyde. What do you think the major product of this reaction will be? And let's say if it's catalyzed by a base. 95% of the time you're going to use a base to make this work. So the first thing I would do is draw the aldehyde facing the left side, but using a line structure. And the first thing I'm going to do is I'm going to use hydroxide. But for the sake of practice, I'm not going to use the carbanion intermediate. This time I'm going to use the enolate ion. So hydroxide is going to grab a hydrogen. We're going to form a double bond, and then the carbonyl group is going to break. So here is the enolate ion. And then this can react with benzaldehyde. Now notice that benzaldehyde doesn't have any alpha hydrogens. The hydrogen that's directly attached to the carbonyl group, the aldehyde hydrogen, that's not an alpha hydrogen. And there's no hydrogens on this carbon, so benzaldehyde cannot be the nucleophile. It's going to be the electrophile. It's going to get attacked by the other aldehyde. So make sure you see that. So here, this is going to turn into a carbonyl group. This double bond is going to attack here, and then those two will connect. So this is going to be carbon 1, 2, and then 3. So that's the first carbon, second, third, and then we have a benzene ring. Now keep in mind, carbon 2 has its methyl group, so I'm just going to put it facing in the downward direction. And we have an O minus, so then notice that when hydroxide grabbed the hydrogen, it turned into water. So we're going to use water to protonate this oxygen, regenerating our hydroxide-based catalyst. And so we have this compound. So now what we can do is we can use hydroxide to remove the alpha hydrogen, which will eventually get rid of the OH group. So now this is going to form a double bond, causing this to move here, expelling the OH. So we get an alpha beta unsaturated aldehyde, and it's conjugated with the benzene ring. So that's going to be the product for that reaction. So now what if you were to see benzaldehyde reacting with hydroxide, and there's no other aldehydes present? What's going to happen now? And we need to consider the fact that there's no alpha hydrogen, so the aldol reaction can't occur. Whenever you have an aldehyde without any alpha hydrogens, in the presence of a base, you get something else, the Cannizzaro reaction. So what's going to happen is the aldehyde will still react with itself, but by means of a different mechanism. Because there's no alpha hydrogens to remove, the hydroxide has no choice but to act as a nucleophile. So it's going to attack the carbonyl instead. And so we have a hydrogen and an OH group. And then in the next step, this oxygen with a negative charge is going to form a double bond, and it's going to do something strange. It's going to kick out a hydride ion, which is going to attack the adjacent aldehyde. And so for the compound on the left, we're going to get a carboxylic acid. And for the one on the right, we're going to get an oxygen with a negative charge. Now, this reaction occurs under basic conditions. So at this point, this oxygen, since it's very close to the other compound, it can grab this hydrogen. And so you can get a carboxylate group. That's going to be one of your answers. And then the other one is an alcohol. Now granted, this oxygen can also grab a hydrogen from water, and hydroxide can remove this hydrogen. We can do that too, but the end result will still be the same. It really depends on which molecule is in the right position at the right time. So the net result of this reaction, let's review. So two benzaldehyde molecules react with each other, and one is oxidized from an aldehyde to a deep protonated carboxylic acid. If we add H3O+, then it's going to become an OH. But under basic conditions, it will remain in this form. And then the other aldehyde is reduced to an alcohol. So whenever you have one molecule, or the same kind of molecule, where one of them is oxidized and the other is reduced, this one is oxidized and this one is reduced, this is known as a disproportionation reaction, where the same species is oxidized and reduced. So here's the next problem. Let's say if we have this particular compound, and we're going to add sodium ethoxide in ethanol. Now there's a lot of carbons. So what do you think is going to happen here? What is this reaction? So here we have an ester in the presence of a base. Whenever you have an ester and a strong base mixed together, especially when this part of the ester matches the base, what you're going to get is the Claisen ester condensation reaction. So let's redraw it this way. This group is ETO. It's an ethyl with an oxygen. So you might have seen it like this. So I'm guessing at this point it looks more familiar. Now this methyl group, I'm going to draw it facing downward. You're going to see the advantage of that soon. So in the first step, this group here is known as OET-. That's sodium ethoxide. The sodium we don't have to worry about. So the ethoxide ion is first going to remove a hydrogen. Now I'm going to draw the carbanion form rather than the enolate form. And then once we get this carbanion, this is going to react with another ester. So this is going to attack the carbon, and then that's going to open. And then you simply connect them. But you connect this carbon, the alpha carbon, with the carbonyl carbon. And so, as you can see, this methyl is not part of the chain. That's why I drew it in a downward direction. And then in the last step, this is going to reform, and we're going to kick out OET. So this is the final product. Now, granted though, if you get a very detailed question, this product doesn't remain in its form. You need to understand that the pH of the solution is very high. because we have a strong base. And this hydrogen is even more acidic than this one. So for an ester, the alpha hydrogen attached to an ester, I believe the pK is like 25. For a ketone, it's 20. For an aldehyde, it's 17. But for a beta keto ester, the pKa is around 11. So this hydrogen is much more acidic. So ethoxide will immediately remove that hydrogen. So your final answer, really, under basic conditions, looks like this. It's going to be a carbanion. So let's review. So let's put this together. Let's summarize what we just learned right now. So if you have two esters reacting with each other, and if you use sodium ethoxide dissolved in ethanol, so just know that ETOH is there. Your final product, like the major product in the solution, looks like this. You're going to have a carbanion. That's your final product. However, let's say if in the first step you add NaOET, and then in the second step you add HCl, because sometimes you might be wondering, what is this? What's the point of adding this HCl at the end? The purpose of that HCl is to protonate this carbanion. And it also protonates the OET group. So you're going to get the answer that you want. So the alpha hydrogen will be there. And this OET group is going to be protonated into ethanol, which means the reaction stops. So this is your final answer after you acidify the solution. So you need to add just enough HCl to pretty much bring the pH from an alkaline solution back down to like a neutral solution, or maybe slightly acidic. If you have an ester, keep in mind, and if you add a very, very strong acid to it, like H3O plus with heat, that ester will convert to a carboxylic acid. So for the Claisen ester condensation reaction, we don't want to add too much acid to it. We don't want to add H3O plus if we want the beta keto ester. If you're wondering what the beta keto ester is, it's the answer that we had in the last problem. So this is an ester. Here's the alpha carbon, this is the beta carbon, there's a ketone on the beta carbon. Let's say if you get this reaction, NaOD with D2O. What do you think is going to happen? This reaction is known as a deuterium exchange reaction. So the OD minus, which works like hydroxide, removes the hydrogen. And then the carbanion is going to act as a base. It's going to get another hydrogen, but the isotopic form of hydrogen. So it's going to get deuterium from water. So basically, we're replacing hydrogen with deuterium. So remember, chemically speaking, hydrogen and deuterium are very similar. So that's a deuterium exchange reaction. Now, you got to watch out for questions where you have excess D2O. If you see the word excess, basically the question is telling you to replace all the alpha hydrogens with deuterium. So your answer should look like this. So now, what if you were to see something like this? In the first step, we're going to add sodium ethoxide. And in the second step, we're going to add ethyl iodide. And in the third step, we're going to add H3O plus followed by heat. So I'm going to use heat as I'm going to represent it with a triangle. What would you do in this process? Well, convert it into a line structure. So the CH3O, that's a methyl group. So instead of ETO, we have MEO. So we have an ester and then we have a ketone. So this is a beta ketoester, which is typically the product of a Claisen ester condensation. So in the first step, we're adding methoxide, which we can represent as OMe. Me is for methyl, Et is for ethyl. So in the first step, we're going to remove an alpha hydrogen. And it's easier to use the carbanion form instead of the enolate form. There's less arrows to draw. But you should familiarize yourself with both. Now once we have this carbanion, we're going to add ethyl iodide. And it's better to do this whole reaction using line structures. It makes the whole process a lot easier. So we're just going to add 2 carbons to the alpha carbon. Now keep in mind, there's another alpha hydrogen here. So if we wanted to, we can add the base again and add another alkyl halide, but we're not going to do that. So once we have this group, what we're going to do now is we're going to add H3O+. H3O+ will convert the ester functional group into a carboxylic acid. Remember what we talked about earlier. Anytime you add water to an acid derivative, like an ester, acid chloride, and hydride, you're going to get carboxylic acid. So now we have a beta keto carboxylic acid. Now once you add heat, decarboxylation will occur at the carboxylic acid if there's a beta keto group. So if there's a carbonyl group on a beta carbon, decarboxylation will occur. And so that's what's going to happen. And so we get a ketone. This reaction is known as it's related to the acetoacetic ester synthesis reaction. Now granted, this is not the acetoacetic ester, but it would be if we had an ETO group instead of a MEO group. But it works the same way because we have a beta keto ester. And so this reaction is very good for making substituted ketones. So this is a ketone. We can make cyclic ketones if we want as well. So what about this reaction? Go ahead and see if you can work through the mechanism and predict the major product for this reaction. So what I would do is I would redraw it. You need to realize that this is an ethyl group, and so is that. That's an OET group. So we have 2 OET groups. So basically, this is the malonic ester reaction. But it works very similar to the acetoacetic ester reaction. The end result is instead of getting substituted ketones, you get substituted carboxylic acids. So this is an OET group. So that's the base. That's going to basically start everything. And just like before, we're going to remove the hydrogen. Now, early in this video, I talked about that. I mentioned that we're going to talk about how to make different amino acids. This is the reaction that you want to use. So now that we have this carbanion, by the way, this is the R group we're going to add. So I'm going to write this as a generic R group. But for now, I'm going to use propyl bromide. So this carbanion is going to attack the propyl bromide, and we're going to add a 3-carbon R group. So here it is. In our next step, once we add the R group that we want, we can add H3O+, and it's going to convert both esters into a carboxylic acid. Now the next step is going to be decarboxylation. We're going to add a heat. Now heat is going to remove one of them. I'm going to remove this one so you can easily see how to draw the final product. So then we get a carboxylic acid with 4 extra carbons. So 1, 2, 3, 4. Now, the R group that we added were these 3 carbon atoms, which is right here. So here's the alpha carbon, and then here's the R group. Now let's talk about how to make amino acids here. Now let's say if we were to do the HVZ reaction, where in the first step we added PBr3, and in the second step we added Br2 with H+. The PBr3 replaces the OH with a Br. And then the second step, the Br2 with H+ replaces an alpha hydrogen with a bromine. And in the third step, when we add water, the bromine that was here, the acid bromine converts back into an carboxylic acid. So the net result of the HVZ reaction is that we're going to replace an alpha hydrogen with a bromine atom. Then if we want to, we can add NH3 to displace the bromine atom. So now we have an amino acid. Eventually this hydrogen will be removed. But I'm going to redraw it though. So here is our amino acid. And this is the chiral carbon here. So let's draw everything around that carbon. So we have a carboxylic acid group, which I'm going to put on the right side. Under neutral pH, the hydrogen will leave. Then we have this NH3 group, which I'm going to put on the left side. There's one hydrogen here. And then this 3-carbon atom that we added, that was the propyl group. That was the R group. So here you can make almost any amino acid, as long as it starts from a primary alkyl halide. So this R group could be anything. So let's say if we wanted to synthesize, let's see, I don't know all the amino acids by memory, but let's say if we wanted an amino acid that looks like this. In the malonic ester synthesis reaction, here's all the steps that we need to make that amino acid. So starting from the malonic ester, in the first step, we can add NaOET. Now the second step, you want to add the R group. So in this case, if I remember what I drew before, I believe it was something like this. So I'm just going to write RBr. Just make sure it's primary though, because if it's secondary, we'll get an E2 reaction rather than an SN2 reaction. And then we can add H3O plus with heat. So that's going to give us our carboxylic acid. Then we're going to do the HVZ reaction, PBr3, and then in the fifth step, we're going to add Br2 with H+, and then water. And at that point, we're going to have our amino acid. So we're going to have a carbon, the carboxyl group, the amine group, a hydrogen, and the R group. In this case, the R group is whatever you have here. Just make sure it's a primary alkyl halide. So here we have 1, 2, 3, 4, 5 carbons. So 1, 2, 3, 4, 5, and the methyl as well. So that's the amino acid that we just created. It all starts from the malonic ester synthesis reaction. So now the next thing we need to talk about is the Robertson annulation reaction and the Michael reaction. So we're going to combine the two together. The Robertson annulation reaction is the Michael reaction plus a cyclic intramolecular aldol reaction. In a Michael reaction, we have a Michael donor and a Michael acceptor. Usually the Michael donor is just a regular ketone, and the Michael acceptor is usually the conjugated ketone. The donor tends to be nucleophilic, and the acceptor tends to be electrophilic. So there's an alpha hydrogen here. The alpha carbon is usually the nucleophilic carbon. So if we were to use a hydroxide-based catalyst, as you can see, we can put a negative charge on this carbon. So that's the Michael donor, the nucleophile, or the nucleophilic carbon. Now for the Michael acceptor, we can move this double bond here and draw the resonance structure. So we can see that the beta carbon is the electrophilic carbon. It has the positive charge. So this is the beta carbon, this is the alpha carbon. Now granted, there's an alpha hydrogen here, so that alpha carbon is also nucleophilic, because we can also draw it this way. So we can put a negative charge on this alpha carbon. So this particular carbanion could react with this acceptor, and that acceptor can also react with itself. But we're going to focus on just these two. And who knows, maybe we'll do an example with this one. So after we remove the alpha hydrogen, and when we get the carbanion, we're going to react it with the Michael acceptor. So the carbanion is going to attack the beta carbon, causing this to move in here, and we're going to get the enolate ion. So now, what's going to happen next is the enolate ion is going to react with water. Since hydroxide took away the alpha hydrogen, it was converted to water. And then we're going to regenerate our hydroxide catalyst. So the product of a Michael reaction is typically a 1,5-dicarbonyl compound. So here we can see the hydrogen. So once we get the 1,5-dicarbonyl compound, now it's going to be the second part of the Robertson annulation reaction, where we're going to get a 6-membered ring. The second part of the Robertson annulation reaction is a cyclic intramolecular aldol reaction. So we can remove any of the alpha hydrogens on the right or left side. It's going to give us a 6-carbon ring. We don't want to remove this alpha hydrogen because when it attacks here, we're going to get a 4-carbon ring. So we're not going to do that. 6-carbon rings are much more stable than 4-carbon rings. So hydroxide is going to grab the hydrogen, and we're going to generate the carbanion. And then this is going to attack the ketone. So when you count it, start by counting from here. 1, 2, 3, 4, 5, 6. So we're going to get a 6-carbon ring. Now I'm going to make this carbon, let's see. I want this carbon to be number 2. This is going to be 1, 3, 4, 5, 6. So on carbon 6, we have an oxygen with a negative charge. On carbon 2, we have a ketone. And on carbon 6, we also have a methyl group. So notice that hydroxide grabbed the hydrogen. So it's now in its protonated form. It's water. So then this oxygen is going to grab a hydrogen from water, regenerating hydroxide. And so now we have our aldol product, which is a carbonyl plus an alcohol. So in our next step is the E1CB reaction. We're going to use the hydroxide we just generated to form the enolate ion. So now we're going to expel the hydroxide ion. This oxygen is going to reform the carbonyl group. That double bond is going to move here, and the hydroxide is going to be kicked out by means of the E1CB reaction. And so we have our final answer. This is an alpha beta unsaturated ketone. So here's the alpha carbon, this is the beta carbon. But now sometimes you have to go backwards. Let's redraw this compound like this. So this is the same compound. The methyl group is where the double bond was. It's flipped. But let's say if you're given this conjugated ketone, how can you find the Michael donor and acceptor that created it? How can you go backwards? If you need to go backwards, what you want to do is identify the alpha beta bond and then cleave it. So whenever you have a conjugated ketone, you need to know that's the product of the cyclic intramolecular reaction, the cyclic aldol reaction. If it's in a ring. If it's not in a ring, then it's just a product of the aldol reaction. So once you cleave it, you're going to get a ketone on the beta carbon. So after you cleave it, make sure you put a ketone on the beta carbon. The alpha carbon just had a hydrogen, but we don't have to show that. So remember, the product of the Michael reaction is a 1,5 dicarbonyl compound. As you can see, we have that. So what I would do at this point is redraw the 1,5 dicarbonyl compound like this. Now, we can choose any ketone. So relative to the ketone on the left side, this is the alpha carbon, this is the beta carbon. We could look at it the other way, but due to symmetry, it doesn't matter which direction we choose from. Now, you want to cleave the alpha beta bond. And so on the left, we have the Michael donor because it just have the alpha, it only has the alpha carbon. And on the right, we have the Michael acceptor. So when you draw the compound on the right, because it has the beta carbon, that's where you're going to put the double bond between the alpha and the beta carbon. And so that's how you can start with your original Michael donor and Michael acceptor. Let's do one more example. So here's another example for the sake of practice. So let's say if you have an aldehyde and a conjugated aldehyde with hydroxide as a base catalyst. Propose a mechanism for the formation of a 6-membered ring. See what product you get. Try it on your paper. So the first thing we need to realize is that we have an alpha hydrogen here. And so the base is going to get rid of that hydrogen. So now we have a carbanion. And this carbanion is going to attack the beta carbon, pushing this double bond here, giving us an enolate ion. So we're going to connect carbon 1 and then 2. 3 is going to be the beta carbon, and then 4, 5. So we're going to have a methyl on carbon 3. So the structure that we have is going to look like this. So on carbon 5, we have an oxygen with a negative charge. This is going to be a double bond between 4 and 5. And on 3, we have the methyl group. So our next step is to add water. And we're going to regenerate the aldehyde functional group. So this is the product of the Michael reaction, which is the first part of the Robinson annulation reaction. We have a 1,5 dicarbonyl compound. You know what? I want to change this a little. I need a ketone on one side, so let's make this a methyl group. So this is going to be a CH3. Because usually the Robinson annulation reaction works if you have a 6-carbon ring. And I realized I had a total of 5, so I'm going to modify it a little. So there's an alpha hydrogen on this carbon. And we still have a methyl group, so I actually had a total of 6, but the methyl was on the wrong side. So now we're going to use hydroxide again and perform a cyclic aldol reaction. So this carbanion is going to attack the aldehyde group, and we're going to count it from the carbanion to the aldehyde. So we're going to get a 6-carbon ring. So on carbon 2, we have a ketone. I'm going to make this 2, 1, 3, 4, 5, 6. And on carbon 1, we have an oxygen with a negative charge. So at this point, protonation will occur. You know what? I'm going to flip it. I'm going to put the ketone over here and the OH on the other side. It's the same, by the way. So now in our next step, we're going to use hydroxide to remove the alpha hydrogen. And then this is going to move here, and then that's going to form a double bond. And I believe I forgot a methyl group somewhere. The methyl group was on, I almost forgot what carbon it was. I believe it was carbon 3. It's one of those carbons. So let's assume it's on carbon 3. If you know which one is the right one, I forgot, you know how to fix it. But at this point, the OH group is going to leave. So we're going to have an alpha beta unsaturated ketone. So that's the product. So now let's work backwards. Let's see if we can get the original Michael donor and acceptor. So this is the alpha beta carbon. We're going to split the alpha beta carbon. Now, on the beta carbon, we're going to add a double bond O. So this is the 1,5 dicarbonyl compound that we have. So I'm going to redraw it like this. Now at this point, we can, and there's a methyl on carbon 3. So at this point, we can break it two different ways, relative to the aldehyde and relative to the ketone. So let's do it relative to the aldehyde. So this is the alpha carbon of the aldehyde, this is the beta carbon. So we're going to cleave the alpha beta bond. So on the left side, we have the 2-carbon aldehyde that we started with. On the right side, we have the ketone. And between the alpha and beta carbon, we're going to put a double bond. So that was the original compound that we had, which it looked like this. Now let's say if we did it the other way. Now let's say relative to the ketone, this is going to be the alpha carbon, and this is the beta carbon. So we can cleave it here. So we have acetone as the donor, and as the acceptor, we have a 4-carbon aldehyde, but we're going to put a double bond between the alpha beta carbon. So these two, this ketone and this conjugate aldehyde can also give you the same product. So you can try it out with a mechanism if you want. But sometimes you might get some unusual microreactions. So what's going to happen here if we put these two together using a base catalyst? So you need to know which one is going to act as the Michael donor. So usually the conjugated one, which is this conjugated nitrile, that's likely to behave as the Michael acceptor. In fact, it has to be the Michael acceptor. Now here we have an alpha hydrogen. And the nitro group is a very powerful electron withdrawing group. So this hydrogen is probably the most acidic one. So that's going to be the Michael donor. By the way, we also have a hydrogen here that is allylic to this double bond, and which is conjugated with the nitrile. So a base could remove this hydrogen, but we're not going to focus about that. We're not going to focus on that hydrogen. Let's keep it simple. On a test, if you see these two compounds, they want you to remove the hydrogen on the nitro group. The alpha hydrogen on the nitro compound. So we have a carbanion. The nitro group looks like this. As you can see, the carbanion is stabilized by resonance. This carbanion can put a negative charge on the oxygen. And so that's why the hydrogen is relatively acidic. If we were to use the other compound, let's say if we remove the hydrogen and put the negative charge here, the negative charge can delocalize and go on a nitrogen. A nitrogen with a negative charge is a much stronger base than a carbon with a negative charge. Than an oxygen with a negative charge. So it's better to put the negative charge on the oxygen than on the nitrogen, which means that this hydrogen is likely to be more acidic. So starting with this carbon anion, we're going to react it with the Michael acceptor. So this is going to attack the beta carbon. This is going to move here, and we're going to put a negative charge on the nitrogen. So let's see how we can redraw this. So I'm going to put the NO2 group here. And then this is the beta carbon, the alpha carbon, and then the carbon with the nitrile. So on the beta carbon, we have a methyl group, which is right here. We have a negative charge on the nitrogen, and we also have a double bond here as well. So our last step is to use water. This nitrogen is going to use this lone pair to reform the nitro group, causing this to grab a hydrogen, expelling hydroxide. So our final answer looks like this. So basically, the end result of this reaction is that we connected the two together. We form a carbon-carbon bond, and we got rid of this double bond. So this is the final answer of that microreaction. Consider this reaction. So let's say if you put these two together. What do you think is going to happen? What is the product of this reaction? Now, you might think that this is a Michael acceptor, and in fact, it can behave as a Michael acceptor. And notice that there's no hydroxide, there's no base catalyst to remove an acidic alpha hydrogen. And also, there's no carbonyl groups or no powerful electron withdrawing groups to stabilize the carbanion. However, we do have a diene, and this is a dienophile. So this is not a microreaction, this is a Diels Alder reaction. So I wanted to throw that in there because you have to watch out for these things. Because this looked like a Michael acceptor, which it can be under the right circumstance. So if you have your diene, you want to redraw it like this. So here's the 4 carbon atoms of the diene. There's a methyl group here and here. And your dienophile, start with your double bond. You have a nitrile on one side and a methyl group on the other side. So we're going to get a 6 carbon ring. And so this is going to be the product. We have a cyanide on one side and a methyl group on the other side. And we can get the enantiomer as well. So what do you think is going to happen if you add sodium methoxide to this compound? The first thing I would do is redraw it. On a test, you might see it as a condensed structure, but I would draw it as a line structure. This is the cyclic Claisen ester condensation reaction, otherwise known as the Deichmann condensation. So what's going to happen is we're going to remove an alpha hydrogen, and we're going to get a negative charge on that carbon. And then this carbanion is going to attack this carbonyl compound, and we're going to get a 5-membered ring. So let's make this carbon 1. Let's see, carbon 2, 3, 4, and 5. So on 5, we have an oxygen with a negative charge, OMe group, or an OCH3 group. And then on carbon 1, we have an ester. So this is going to reform into a carbonyl group, and we're going to expel methoxide. So as we can see, we have a beta keto ester with the ketone on a ring. So that's the product of the Deichmann condensation. Now, if we add H3O+, if we wanted to, we can convert the ester into a carboxylic acid. And then if we add heat, decarboxylation can occur, and we can remove the carboxylic acid, so we can make cyclopentanol. So that's the answer for that reaction. Okay, so what we're going to do now is we're going to look at polymerization reactions. And we're going to talk about three types: radical polymerization of alkenes, cationic polymerization of alkenes, and anionic polymerization of alkenes. So let's say if we have an organic radical. If we add heat or ultraviolet light, the radical is going to break apart. So it's going to generate two radicals. And then we can react this radical with an alkene. So for this particular problem, I'm going to draw the bonds so you can clearly see everything. And we need something to stabilize the formation of a new radical. So I'm going to put a benzene ring or phenyl on the right side of the alkene. So the radical is going to react with the left side of the alkene because the phenyl is on the right side. And the reason being is because we're going to get a new radical, and that new radical is going to form where the benzene ring is. And the reason why that occurs is because having a radical on the benzylic carbon, it stabilizes it. So what we have, let's say this is the benzene ring. On the first carbon outside of the benzene ring, we have a radical. And so this radical can resonate inside of the ring, so it's stabilized by the ring. And then the reaction is going to continue. It's not going to stop there. Now, we're going to do enough so that we can quickly draw what the major product will look like. Once we have this radical, and I forgot that there's a phenyl right there, it's going to react with another phenyl group. Another alkene group. And so this radical is going to form a bond with the second alkene, and then the other pi electron is going to go towards the carbon that has the benzene ring, so it can be stabilized as well. So as you can see, we get this compound, and here's the radical. The only reason why I put this phenyl on this side is to avoid like steric strain. But at this point, on a test, you have enough information to find out what the product is going to look like. Notice that this is the repeating unit. So your answer that you're looking for should look something like this. Sometimes you might not see this radical here. Let me redraw it on the next page because I'm running out of space. So you're going to have two carbons. You're going to have a hydrogen, and you're going to have a phenyl, and then the chain can keep one going, and then you're going to have a parentheses because this is the repeating unit, and then you could put N because this can repeat 100 times, maybe 1,000 times, we don't know. But on a test, this is what you're looking for. So anytime you have a radical polymerization of an alkene, it's going to go to an alkane. You're still going to have the four groups of the alkene, and then the double bond is going to turn to a single bond, and you're going to have these two lines extended from it. So now let's talk about the cationic polymerization of alkenes. So for this, we need to add a very powerful Lewis acid or electrophile. Whenever you add an electrophile to an alkene, you're going to get a carbocation. Now we're going to use a phenyl group again because the benzene ring can stabilize a carbocation in the same way that it can stabilize a radical reagent. So this time, the Lewis acid that we're going to use will be boron trifluoride. And the reason why this is effective is because boron already has an empty p orbital. It has 3 bonds, it doesn't have 4. In addition to that, fluorine is a very powerful electron withdrawing group. So it pulls electron density away from an already starving boron atom. Boron really wants electrons and fluorine is taken away from it. So boron has a very, very strong partial positive charge. And so it's going to be very easy for the alkene to react with the boron atom. So here's boron. Now it has 4 bonds, so it's a little bit happier, and it has a negative formal charge. And so we now have a carbocation, and it's on the carbon with the phenyl, so it's stabilized by resonance. And then this can react again. So we can add another alkene to it. And so this double bond will react with that carbocation, and the ring is, not the ring, but the chain is going to continue to grow. So at this point, we can see what the repeating unit is. It's right here. It's the same as what we had in the last example, because we had the same 4 groups around the alkene. So it looks like this. And then we could put an end to it. Now we're not going to go over the termination steps of this reaction. We're just going to go into enough detail so you can get the answer. So now the last one that we're going to consider is an anionic polymerization reaction of alkenes. So instead of adding an electrophile, we're going to add a nucleophile. So the nucleophile that we can use is hydroxide. But for hydroxide to be interested in the alkene, we need we need to add some electron withdrawing groups to the alkene. So let's add an aldehyde to it and a nitro group to it. So both the aldehyde carbon and the nitrogen carbon, they're strong electron withdrawing groups. So this alkene, if we draw the resonance structure, can move here. The nitrogen has a positive formal charge at this point. And so if we were to draw the resonance form, we can see that there's a positive charge on this carbon. So this carbon has a lot of partial positive charge. We can also get that same carbocation if this double bond moves towards the aldehyde. So hydroxide is attracted to this carbon. Okay, so now let's work out the reaction. So I'm going to write just this group as a CHO and this group as an NO2. So the hydroxide is going to attack the electrophilic carbon, and it's going to put a negative charge on that carbon. So we're going to get a carbanion. But this carbanion, keep in mind, is stabilized by 2 very powerful electron withdrawing groups. So the aldehyde is pulling electron density away from the carbanion, and the nitro group is doing the same thing. So now, this can react with another alkene. And it's going to attack it at the electrophilic carbon, which is this carbon, because that's the carbon with the positive formal charge if we draw the resonance structure. So this is going to attack here, and it's going to put another carbanion. We're going to get another carbanion on the last carbon. So see if you can identify the repeating unit. So here we have the carbanion. So the repeating unit is right here. Let me use a different color. So to draw it, it looks like this. So let's work through some examples. So let's say if you want to find a product of this radical polymerization reaction. Let's say if we have a bromine, a chlorine, and a phenyl group. And we're going to use peroxides and some sort of radical initiator. Let's use heat. So put the two carbon atoms and place the four groups exactly the way you see it. So we have a hydrogen, a bromine, a chlorine, and a phenyl group. Then add two lines, one to the left, one to the right. Put a parentheses around those four groups, and then put an N on the outside. That's going to be the major product. So it's always going to be like that. So even if you were to use, let's say, an anionic polymerization reaction, so let's say if we have a CF3 group and let's say an ester group. And on this side, let's say we have a hydrogen and a methyl. And then let's say we add sodium hydroxide. So that's a nucleophile, so it's an anionic polymerization reaction. So first, we're going to get rid of the double bond. We're going to turn it into a single bond. And we're going to write the four groups that we have in the exact same way that we see it. And then we're going to place a bond to the left, to the right and to the left, and enclose it in parentheses. And then place an N. I know I'm out of space, but there should be an N there. So let's try one more example. So let's say if we add an electrophile like BF3. So this is going to be another polymerization reaction, but it's going to be a cationic polymerization reaction because here we're adding an electrophile. So what we're going to do is we're going to convert the double bond into a single bond. Add the four groups. Add two lines, one to the right, one to the left, and then just put an N on the outside of the parentheses. So that's how you can find the four monomeric units for that reaction. So that's the end of this video. At this point, we've covered almost every reaction that you've learned in organic chemistry. If not every reaction, maybe a good majority of it, but enough so that you can do well on your final exam. So thanks again for watching, and I wish you well on that test, and have a great day.